Hello there, and welcome to Science for Sleep, a quiet place where curiosity slows down, explanations take their time, and science is allowed to feel gentle instead of demanding. Tonight, we are drifting far from the warmth of the sun, beyond the familiar orbits of the planets you learned as a child, and into a colder, darker region where gravity speaks more softly, but no less clearly. This is a story about physics, not feelings, though feelings tend to show up anyway. It is about motion, mass, and balance. It is about how objects behave when the sun's grip weakens, and how those behaviours quietly decide what counts as a planet and what does not. The name at the centre of this discussion is Eris, a distant world that spends most of its time so far away that sunlight there is little more than a bright star. Eris did not arrive with fanfare or spectacle. It did not blaze across the sky or announce itself to the public. Instead, it appeared in data, in careful measurements, in repeated observations that refused to go away. And once it was noticed, once its mass and orbit were understood, it forced astronomers to confront a question they had been quietly postponing for years. Not a question about nostalgia or childhood memory, but a question about physics. What exactly makes a planet a planet? Before we move any farther, take a moment to notice where you're listening from tonight. Maybe you're already lying down, maybe the lights are low. Perhaps it is late evening or early morning, or one of those hours that feels detached from the rest of the day. What time is it where you are right now, and what does the sky look like beyond your walls if you could see it? Out there, far beyond the stars you recognise, objects like Eris are moving with extraordinary patience, tracing paths that take centuries to complete a single loop. Nothing is rushed where we are going. If you find this kind of slow, thoughtful exploration calming, or if it helps your thoughts loosen their grip at the end of a long day, you're always welcome to like the video or subscribe to the channel. It helps this quiet corner of science reach others who might need a gentle place to rest their attention. And now, without urgency, let us begin to follow the physics that led to one of the most misunderstood decisions in modern astronomy. For a long time, the solar system felt complete. There were 8 planets, or 9 depending on when you learned them, arranged neatly by distance from the sun. This picture felt stable because it was simple. Each planet followed a mostly circular path, roughly aligned in a single flat plane, like grooves on a record. This was not just a visual convenience, it reflected the physics of how the solar system formed. When the sun ignited, it did so within a rotating disk of gas and dust. Gravity pulled material inward, collisions smoothed out motion, and over millions of years most of the mass settled into a relatively thin plane. The largest objects grew larger by sweeping up their surroundings. Smaller debris was either absorbed, flung away, or trapped in stable regions. This process produced what physicists call dynamical order. Each large body became the dominant gravitational presence in its region. Near the Sun, Mercury controls its narrow zone. Farther out, Jupiter dominates with overwhelming mass, shaping asteroid belts and stabilizing orbits across vast distances. Even Earth, modest compared to gas giants, has enough gravity to clear nearby space of similar-sized competitors. These outcomes are not aesthetic choices. They are the direct result of gravity acting over time, favouring objects that can impose order on their surroundings. For decades, Pluto sat uneasily in this picture. Its orbit is tilted, it is elongated. It crosses Neptune's path rather than staying politely in its own lane. From a physics perspective, this is already a warning sign. Objects that form alongside planets and grow into planetary mass tend to settle into low inclination, low eccentricity orbits. Pluto did not do this. Instead, it occupies a resonance with Neptune, completing 2 orbits around the Sun for every 3 of Neptune's. This resonance keeps Pluto stable, but it also reveals something important. Pluto is not in control, it is being controlled. Resonance is a gravitational negotiation. When 2 bodies repeatedly tug on each other at regular intervals, their orbits can lock into patterns that persist for billions of years. This is not dominance, it is coexistence under constraint. Neptune's gravity shepherds Pluto, preventing close encounters that would otherwise destabilize its orbit. A true planet does not need protection like this. It provides it. Still, for many years, Pluto was treated as an exception rather than a clue. That changed as telescopes improved. In the late 20th century, astronomers began to detect other icy bodies beyond Neptune, moving in similar orbits, with similar compositions. These objects were not rare anomalies, they were members of a vast population now known as the Kuiper Belt. This region is not empty space. It is a disk of debris, a remnant of planet formation that never quite finished. Here, countless icy bodies orbit the Sun, ranging from tiny fragments to worlds hundreds or even thousands of kilometers across. Physics becomes unavoidable once you recognize a population. If Pluto is one of many similar objects, then its classification must reflect that reality. And then Eris was found. Eris is slightly more massive than Pluto. Its orbit is even more extreme, tilted at a steeper angle, and stretched into a long ellipse that carries it far beyond Pluto's path. From a dynamical standpoint, Eris is unmistakably a member of the same family. It does not dominate its region. It does not clear its neighbourhood. It shares space with other objects of comparable size and mass, interacting weakly, slowly, over enormous spans of time. At this point, physics leaves very little room for debate. If Pluto is a planet, then Eris must be one too. And if Eris is a planet, then dozens, perhaps hundreds of similar bodies would eventually require the same designation as surveys improved. The solar system would not have 9 planets, but scores of them, with no clear boundary between planets and debris. This is not how physical classification works. In physics, categories exist to reflect behaviour, not sentiment. This is why the definition of a planet could not remain informal. It needed to be tied to measurable properties. Orbiting the Sun is not enough, because countless objects do that. Being round is not enough, because gravity rounds objects once they exceed a certain mass, regardless of their role in the system. The missing criterion was dynamical dominance. A planet must be massive enough that its gravity has shaped its orbital zone, either by absorbing smaller bodies, ejecting them, or locking them into stable resonances where they no longer compete. When astronomers formalized this definition through the International Astronomical Union, they were not downgrading Pluto out of spite. They were acknowledging what the physics had been saying all along. Pluto and Eris are fascinating worlds. They are geologically complex, rich in ice chemistry, and worthy of study. But they are not the architects of their regions. They are participants, not rulers. This distinction matters because it reflects how the solar system actually works. Gravity does not care about tradition. It responds only to mass, distance, and time. Over billions of years, these factors sort objects into roles. Some become dominant, others remain part of a collective. Eris forced astronomers to stop pretending Pluto was alone, and once that pretense fell away, the structure of the outer solar system became clearer, not poorer. It is enough to rest with the idea that the solar system is not a static list, but a living dynamical system, one where definitions emerge from behaviour and where distant objects like Eris quietly reshape how we understand the whole. When gravity became the language through which planetary order was understood, the solar system stopped being a collection of lights in the sky and began to reveal itself as a physical system governed by rules that do not bend for traditional memory. Long before equations were written down, gravity was already at work, pulling, shaping, sorting, and slowly deciding which objects would matter most. The realization that this invisible force could explain both the fall of an apple and the motion of distant worlds marked a turning point, not only in physics, but in how humans understood their place among those worlds. For most of human history, planets were defined by how they appeared. They were wanderers against a fixed backdrop of stars, lights that moved while others stayed still. This observational definition was sufficient for a sky watched with the naked eye. There were only a handful of objects that behaved this way, and they followed paths that seemed orderly enough to track with patience and geometry. Nothing in that framework required an explanation for why these objects moved as they did. Motion itself was the defining feature. That changed when gravity entered the conversation as a universal principle rather than a local curiosity. With the work of Isaac Newton, gravity became more than a description of falling bodies. It became the connective tissue linking Earth to the heavens. The same force pulling objects downward was shown to extend outward indefinitely, weakening with distance but never vanishing entirely. Suddenly, the planets were no longer exceptions moving through divine mechanisms. They were masses responding to forces just like everything else. Once gravity was accepted as universal, order in the solar system could be explained without invoking special rules for special objects. The Sun, containing more than 99% of the system's mass, exerted overwhelming influence. Objects closer to it moved faster, bound tightly by its gravity. Objects farther away moved more slowly, tracing wide arcs through space. This alone explained why inner planets whip around the Sun in short years, while outer ones take decades or centuries to complete a single orbit. But gravity did not only explain motion around the Sun, it also explained how planets interacted with their surroundings. In a system filled with debris, dust, and smaller bodies, gravity is not passive, it is competitive. Objects that grow slightly larger than their neighbours begin to attract more material. This additional mass strengthens their gravitational pull, allowing them to gather even more material. Over time, this runaway process creates a small number of dominant bodies surrounded by cleared regions. This is not a design choice. It is an inevitable outcome of gravitational dynamics acting over long timescales. This is where planetary order begins to emerge in a meaningful physical sense. A planet is not simply an object that orbits a star. It is an object that has asserted control over its orbital zone. Through collisions, accretion, and gravitational scattering, it has either absorbed nearby material or forced it into stable configurations that no longer compete for dominance. The region around a planet becomes structured, shaped by its presence. This idea becomes clearer when looking at the inner solar system. Earth did not form in isolation. Early on, its orbit was crowded with planetesimals, fragments left over from the protoplanetary disk. Over millions of years, Earth collided with many of them, incorporating their mass. Others were flung into different orbits or driven into the Sun. By the time Earth reached its current state, its orbital neighbourhood had been largely emptied of comparable bodies. What remained were either much smaller asteroids or objects locked into resonances that kept them from becoming rivals. The same pattern holds for the gas giants, though on a much larger scale. Jupiter's immense gravity reshaped vast regions of the solar system. It carved gaps, stabilized Trojan asteroids, and prevented a planet from forming in what is now the asteroid belt by constantly stirring the region and preventing accretion. Saturn, Uranus, and Neptune each did similar work within their own domains. Their masses are not merely impressive numbers, they represent the capacity to impose long-term order. As physics matured, this understanding of gravitational dominance became central. Planetary order was no longer about counting objects or listing names. It was about identifying which bodies mattered dynamically. In equations describing orbital evolution, mass enters directly. A small object responds to gravitational forces, a large object shapes them. This distinction is not philosophical. It determines whether an orbit remains stable, whether collisions increase or decrease over time, and whether a region becomes quiet or chaotic. When astronomers began studying regions beyond Neptune with modern instruments, this gravitational perspective became unavoidable. The outer solar system is not empty. It is filled with objects that orbit the Sun but do not dominate their surroundings. Their mutual gravitational interactions are weak. No single body has enough mass to clear the region or organise it into a simple hierarchy. Instead, it remains a population, not a kingdom. This is where the language of gravity began to conflict with older planetary definitions. If gravity is the organising principle, then classification must follow gravitational behaviour. An object's importance is measured not by familiarity, but by influence. This is why size alone is misleading. A body can be large enough to be spherical, yet still be dynamically insignificant in its orbital zone. Roundness tells us about internal gravity and material strength. It says little about external control. In the outer regions, orbital periods stretch into centuries. Gravitational interactions unfold slowly, but they are no less decisive. Given enough time, dominant bodies reveal themselves through their effects. Their neighbours are gone, displaced, or tightly controlled. Where such dominance is absent, the system remains crowded. This is not a temporary state waiting to resolve. In some regions, the available mass was never sufficient to allow a single object to take over. The outcome is a belt, not a planet. Understanding gravity as the language of planetary order also changed how scientists thought about formation. Planets are not placed, they grow. Their final status depends on initial conditions, available material, and interactions with other growing bodies. In regions close to the Sun, higher densities and shorter orbital times favoured rapid accretion. Farther out, growth was slower, and competition remained unresolved. Physics predicts this outcome without exception. This perspective removes emotion from classification. It does not ask what feels intuitive or traditional. It asks what role an object plays in the system. Does it dominate? Does it shape? Does it impose order? If not, then it belongs to a different category, regardless of how interesting or complex it may be. This is not a demotion, it is a description. As gravity became the guiding principle, planetary science matured into a discipline grounded in dynamics rather than appearance. The solar system transformed from a tidy diagram into a hierarchy shaped by mass and motion. Some objects emerged as architects, others remained as witnesses to an unfinished process. This shift laid the groundwork for everything that followed. Once gravity was accepted as the defining language, older definitions could no longer survive unchanged. Objects like Pluto and Eris did not break the rules, they revealed them. And as the physics became clearer, the solar system itself became more honest, even if it became less simple. Planetary physics learned very early to distrust names. Labels are convenient for conversation, but gravity does not respond to vocabulary. It responds to mass, distance, velocity, and time. When physicists study planets, they are not primarily interested in what an object is called, or how long it has carried that name, or how familiar it feels to human culture. Their attention stays fixed on motion. How an object moves tells you what forces act on it. How that motion changes tells you what role it plays in the system. Over long enough timescales, motion becomes the most honest description available. In everyday language, a name feels definitive. Once something is called a planet, it seems like that status should stick. But in physics, categories are provisional. They exist to describe behaviour, not to preserve tradition. If new observations reveal that an object behaves differently than previously thought, the category must change or become meaningless. This is not a flaw in science. It is how science stays aligned with reality. Motion sits at the centre of this alignment because motion is measurable with extraordinary precision. You can track an object's position night after night. You can calculate its velocity, its acceleration, the subtle shifts in its orbit caused by other bodies. These measurements are not subjective. They do not depend on interpretation in the way visual appearance might. An orbit either precesses or it does not. A body either dominates its region or it does not. Gravity leaves a mathematical signature that cannot be argued with. This focus on motion dates back to the earliest successes of celestial mechanics. When Johannes Kepler derived his laws of planetary motion, he did not define planets by their physical nature. He described how they move, elliptical orbits, equal areas swept in equal times, and predictable relationships between orbital period and distance from the Sun. These laws worked not because of what planets were called, but because they captured the underlying gravitational structure of the system. Later, when Isaac Newton unified celestial and terrestrial motion under a single law of gravity, the emphasis on motion became unavoidable. The equations did not contain the word planet. They contained mass, force, and acceleration. Any object that obeyed those equations, whether a moon, a comet, or a planet, followed the same rules. Classification mattered only insofar as it reflected differences in dynamical role. As telescopes improved, astronomers discovered objects that blurred old categories. Moons were found orbiting planets. Small bodies were found sharing orbits. Some objects followed paths that crossed those of larger bodies without colliding, protected by resonances. In each case, names lagged behind understanding. The physics was already clear, but language took time to catch up. This lag becomes especially important in crowded systems. If you observe a single object in isolation, its name feels sufficient. But when you observe thousands of objects interacting over billions of years, names lose explanatory power. Motion does not. In a gravitational system, what matters is not how an object looks or what it has been historically grouped with, but whether its presence changes the behavior of others. Planetary physics therefore treats the solar system as a dynamical system. This means it is studied as a collection of interacting bodies whose future states depend sensitively on their initial conditions and mutual influences. In such systems, long-term behavior reveals structure that short-term observation might miss. A body that appears stable over decades might reveal instability over millions of years. A region that seems orderly might slowly disperse under weak perturbations. This long view is critical. A true planet is not defined by where it happens to be right now, but by how it has shaped and will continue to shape its orbital environment over geological time. Has it cleared nearby material? Has it established stable zones? Has it prevented other bodies of similar size from persisting nearby? These questions are answered by studying motion, not by assigning titles. Consider orbital crossings. In a naive sense, one might think that two objects whose orbits cross should eventually collide. But in planetary systems, this is often not the case. Resonances can prevent collisions indefinitely. Motion becomes choreographed, not chaotic. One object repeatedly arrives at a critical point when the other is safely elsewhere. This delicate timing is enforced by gravity itself. Understanding this requires equations, not labels. This is why planetary physics pays close attention to resonant motion. When two bodies interact gravitationally at regular intervals, their orbits can become locked into predictable ratios. This can stabilize otherwise precarious configurations. It can also destabilize regions, stirring up debris and preventing accretion. Whether an object participates in such resonances as a controller or as a participant tells you a great deal about its role. Mass enters these equations directly. A more massive body exerts stronger perturbations. It shifts resonance locations. It alters precession rates. It creates gaps in debris disks. These effects scale with mass in ways that are precisely calculable. No amount of naming can substitute for that influence. If an object lacks the mass to produce such effects, it will not behave like a planet, regardless of what it is called. The importance of motion over naming becomes especially clear in regions beyond the major planets. In the outer solar system, orbital periods are long and interactions are subtle. Objects may take hundreds of years to complete a single revolution. Small perturbations accumulate slowly. To understand these regions, astronomers simulate millions or billions of years of motion, tracking how orbits evolve. In these simulations, labels are irrelevant. Only trajectories matter. When such simulations are run, patterns emerge. Some objects remain isolated and stable. Others cluster into populations. Some are scattered inward or outward. Some are ejected entirely. These outcomes depend on initial conditions and gravitational interactions, not on categorical decisions. If an object consistently behaves as part of a population rather than as a dominant body, planetary physics treats it accordingly. This approach can feel counterintuitive because human intuition is drawn to discrete categories. We like clean lists. We like boundaries that do not move. But gravitational systems are not obligated to respect those preferences. They are continuous. They produce gradients rather than sharp divisions. Planetary classification is therefore an attempt to impose useful structure on a system that does not naturally divide itself into tidy bins. Physics tolerates this imprecision only as long as categories remain predictive. A good classification allows you to anticipate behavior. If calling something a planet leads you to expect certain gravitational effects that do not occur, the classification has failed. At that point, it must be revised, not defended. This is exactly what happened as more objects were discovered in the outer solar system. Bodies once thought exceptional were revealed to be representative. Their motions matched those of a broader population. Their mass was insufficient to dominate. Their orbits were shaped by larger neighbours. From a dynamical standpoint, they were not planets in the same sense as Earth or Jupiter. Keeping the name would have obscured that reality. Another reason motion matters more than names is that names are static, while motion is dynamic. A name suggests permanence. Motion reveals process. Planetary systems evolve. Orbits migrate. Resonances shift. Bodies collide or are ejected. A classification that ignores this evolution risks becoming misleading. Planetary physics is therefore cautious about freezing definitions too early. This caution extends to formation theories. How an object formed is often inferred from how it moves now. Objects that formed in situ tend to have low inclinations and circular orbits. Objects that were scattered tend to have higher inclinations and eccentricities. These signatures persist long after formation is complete. By reading motion, physicists reconstruct history. Names cannot do this work. Calling something a planet does not tell you how it formed or how it will behave in the future. Motion does. This is why the equations of motion remain central even as observational technology improves. Better telescopes give you better positions. Better positions give you better orbits. Better orbits give you better understanding. The emphasis on motion also explains why planetary physics is comfortable with uncomfortable conclusions. If the data say an object does not dominate its region, that conclusion stands regardless of public reaction. Physics is not democratic. It does not negotiate. It responds only to evidence. At the same time, this does not mean that names are useless. They are tools for communication. They help organize knowledge. But in physics, tools are judged by utility, not sentiment. When a name stops helping and starts confusing, it must be adjusted. This principle applies beyond planets. It applies to stars, galaxies, particles, and phases of matter. In every case, classification follows behavior. A star is not defined by brightness alone, but by nuclear fusion. A particle is not defined by analogy, but by interaction. Consistency demands the same rigor for planets. As this perspective took hold, the debate over planetary status shifted away from emotion and toward mechanics. The question stopped being, "What have we always called this?" and became, "What does this object do?" That shift was not sudden, but it was decisive. Once planetary physics committed fully to motion as the primary criterion, certain outcomes became inevitable. Objects whose orbits revealed dependence rather than dominance could not remain in the same category as those that shaped the system. This was not a judgment. It was a description. Motion remains the guide. Orbits stretch, tilt, and intertwine. Time lengthens. Interactions slow. And within that slow dance, the logic of planetary physics continues to unfold, indifferent to names, steady in its insistence that how something moves will always matter more than what we choose to call it. For a long time, the solar system was treated as a list, a tidy sequence of names arranged by distance from the Sun, memorized in classrooms, printed in textbooks, recited until it felt permanent. Mercury, Venus, Earth, Mars, then the giants, and once upon a time, Pluto at the end like a punctuation mark. Lists are comforting because they imply completion. They suggest that everything important has been identified, categorized, and placed where it belongs. Physics, however, has very little interest in lists. What it sees instead is a system, and systems behave in ways that lists cannot describe. A dynamical system is not defined by what it contains, but by how its components interact over time. In physics, this means focusing on forces, feedback, stability, and change. When the solar system is approached this way, the emphasis shifts immediately. Names fade into the background, and motion takes center stage. Objects are no longer important because they appear on a diagram, but because of how they exchange energy and momentum with everything around them. The Sun dominates this system by mass alone. Containing nearly all the mass available, it establishes the gravitational framework within which everything else moves. But dominance by mass does not eliminate complexity. Every planet, moon, asteroid, and distant icy body contributes, however slightly, to the gravitational web. Over short timescales, many of these contributions are negligible. Over millions or billions of years, they accumulate into meaningful change. This accumulation is why the solar system cannot be understood as static. Orbits are not frozen tracks carved into space. They are solutions to equations that evolve as conditions change. A small gravitational nudge, repeated often enough, can reshape an orbit entirely. In a list-based mindset, these subtleties disappear. In a dynamical framework, they are the entire story. One of the clearest examples of this comes from orbital resonance. When two objects orbit the Sun with periods that form a simple ratio, their gravitational interactions repeat in a regular pattern. These repeated interactions can stabilize or destabilize orbits depending on circumstances. Resonances can protect objects from collisions or push them into chaotic motion. The presence of such resonances reveals a system actively organizing itself through gravity, not passively following predefined paths. If the solar system were merely a list, these resonances would be curiosities. In a dynamical system, they are structural features. Jupiter's resonances sculpt the asteroid belt, creating gaps where objects cannot persist. Neptune's resonances shape the orbits of distant icy bodies, locking them into patterns that last for billions of years. These effects do not require intention or design. They emerge naturally from repeated gravitational interaction. Another key feature of dynamical systems is sensitivity to initial conditions. Small differences early on can lead to very different outcomes later. During the solar system's formation, countless bodies interacted in a dense disk of gas and dust. Tiny variations in mass, position, or velocity determined which objects grew into planets and which remained fragments. Once these outcomes were set, gravity reinforced them, amplifying early advantages into long-term dominance. This perspective explains why the solar system contains both orderly regions and messy ones. The inner region, close to the Sun, is relatively clean. The major planets occupy well-separated orbits with little competition nearby. Farther out, especially beyond Neptune, order gives way to population. Many objects share similar regions, none massive enough to impose complete control. From a list perspective, this looks like an anomaly. From a dynamical perspective, it is exactly what the physics predicts. Lists struggle with populations, they prefer singular representatives. But dynamical systems often produce families rather than individuals. The asteroid belt is not a failed planet in a narrative sense. It is a region where gravitational stirring prevented accretion. The Kuiper Belt is not an afterthought. It is a reservoir of material that never consolidated into a single dominant body. These outcomes follow directly from gravitational interaction and available mass. When astronomers began discovering large numbers of objects beyond Neptune, the inadequacy of a list-based approach became obvious. Adding names did not increase understanding. What mattered was how these objects moved relative to each other and to the known planets. Their inclinations, eccentricities, and resonant relationships told a coherent story that a list could not capture. Dynamical systems are also defined by stability and instability. Some configurations persist for billions of years. Others are temporary, slowly unravelling under weak perturbations. Determining whether an orbit is stable requires long-term simulation. It cannot be answered by a snapshot. Physics therefore treats the solar system as something unfolding, not something finished. This unfolding nature becomes especially important when considering migration. Early in the solar system's history, the giant planets did not necessarily form where they are now. Interactions with the surrounding disk and with each other likely caused them to shift inward or outward. These migrations would have dramatically reshaped the distribution of smaller bodies, scattering some regions and emptying others. Evidence for this process remains encoded in present-day orbits. A list does not migrate, a system does. Understanding why certain regions are populated and others are sparse requires acknowledging that planets themselves moved. Their gravity acted like a snowplow, reshaping the system as they travelled. This dynamic history explains features that would otherwise seem arbitrary. Another hallmark of dynamical systems is hierarchy. Not all components exert equal influence. Some objects act as drivers, others as responders. In the solar system, planets occupy the upper levels of this hierarchy, while smaller bodies fill in below. But even among planets, influence varies widely. Jupiter's mass makes it a dominant player far beyond its immediate orbit. Mars, by contrast, has relatively little influence outside its narrow zone. This hierarchy is not reflected well by a simple list. Listing planets side by side implies equivalence. Dynamics reveals disparity. Some bodies shape the system, others are shaped by it. Classification that ignores this difference risks flattening meaningful structure. The recognition of the solar system as a dynamical system also changes how scientists think about boundaries. In a list, boundaries are sharp. An object is either included or excluded. In a system, boundaries are fuzzy. There are transitional regions where behaviour changes gradually rather than abruptly. The distinction between planets and smaller bodies is one such boundary. From a dynamical standpoint, this boundary is defined by dominance, not by size alone. Objects above a certain threshold impose order. Below it, they remain part of a population. The threshold is not arbitrary, but it is not infinitely precise either. It depends on local conditions and timescales. This is why classification debates arise at all. Physics accepts this ambiguity because it reflects reality. Nature does not draw lines for convenience. It produces continua. The job of science is to describe those continua as accurately as possible, even if that means accepting categories with edges rather than walls. Seeing the solar system as a system also highlights the importance of timescale. Human intuition operates on years or decades. Gravitational systems operate on millions of years. Processes that seem negligible within a lifetime become decisive over geological time. Weak interactions accumulate. Rare events matter. For example, a small change in orbital eccentricity might seem trivial now. Over millions of orbits, it can lead to close encounters, collisions, or ejection from the system entirely. Dynamical analysis captures this long-term evolution. Lists do not. This timescale difference also explains why reclassification can feel disruptive. A list suggests permanence. A system suggests ongoing refinement. As observations improve and simulations extend further into the future and past, understanding deepens. Categories must adjust accordingly. Importantly, treating the solar system as a dynamical system does not diminish its wonder. If anything, it enhances it. Instead of a static display, we see a living structure shaped by gravity's persistent influence. Patterns emerge not because they were designed, but because they are stable solutions to physical laws. Within this framework, objects like Pluto and Eris become more meaningful, not less. They are no longer awkward entries at the end of a list. They are representatives of a population that tells us about conditions in the early solar system and about the limits of planetary growth. Their orbits preserve information that dominant planets erased in their own regions. This is why physics insists on motion over memory. A list remembers what we once thought mattered. A dynamical system reveals what actually matters now. The solar system did not change when definitions changed. Our description of it did. Pluto's orbit presents a problem only if you expect the solar system to behave like a neatly arranged diagram. Once motion is taken seriously, the problem becomes something else entirely. It becomes a lesson. Pluto does not travel around the Sun in the quiet, orderly way that the major planets do. Its path is tilted, stretched, and strangely synchronized with a much larger neighbor. None of this is accidental, and none of it can be understood by looking at Pluto alone. The explanation lives in resonance, one of the most revealing concepts in orbital physics. To begin with, Pluto's orbit is highly eccentric. Instead of tracing a near circle, it follows a long ellipse that carries it from deep beyond Neptune's average distance to a point closer to the Sun than Neptune itself. For part of every orbit, Pluto is technically inside Neptune's path. If orbital diagrams were traffic maps, this would look like a guaranteed collision waiting to happen. Yet collisions never occur. Pluto and Neptune have been locked in this configuration for billions of years without incident. That stability is the clue. The second striking feature is inclination. Most planets orbit within a few degrees of the same flat plane, a remnant of the original protoplanetary disk. Pluto does not. Its orbit is tilted by more than 17 degrees relative to that plane. From a formation perspective, this already places Pluto in a different dynamical category. Objects that grow into dominant planets tend to damp out inclinations through repeated interactions with surrounding material. Pluto never did. Its orbit preserves evidence of a more chaotic environment. Then there is the most important feature of all. Pluto is in a precise 3:2 orbital resonance with Neptune. For every 3 times Neptune orbits the Sun, Pluto orbits exactly twice. This is not approximate. It is exact within measurable limits, maintained by gravity with relentless consistency. Resonance of this kind does not happen by chance, and it does not happen without consequence. Resonance occurs when gravitational interactions repeat at regular intervals. Each time Pluto and Neptune reach particular points in their orbits, Neptune's gravity gives Pluto a small nudge. One nudge alone would mean little, but when the timing repeats perfectly, those nudges add up. Over time, they shape the orbit into a stable configuration that avoids close encounters. In Pluto's case, resonance ensures that whenever Pluto crosses Neptune's orbital distance, Neptune is far away. The geometry is locked in. This is not Pluto asserting control. It is Pluto being controlled. In a planetary system, resonance can serve 2 very different roles. A massive body can impose resonances on smaller objects, shaping their motion across wide regions. Jupiter does this in the asteroid belt, carving out gaps where objects cannot survive. Neptune does this in the outer solar system, trapping objects into stable resonant orbits. The smaller bodies do not choose these configurations. They are shepherded into them by the dominant planet's gravity. Pluto belongs to a class of objects known as Plutonos, all of which share this same 3:2 resonance with Neptune. Pluto is simply the largest and most famous member. From a dynamical perspective, it is not unique. It is representative. Its orbit tells the same story as dozens of other bodies that follow similar paths, though none with the same public recognition. This realization is deeply uncomfortable if you approach the solar system as a list. Lists prefer exceptions to be rare. But physics is indifferent to fame. When a supposedly unique object turns out to be part of a population, the population becomes the more important fact. Resonance reveals population structure with unforgiving clarity. The origin of Pluto's resonance likely traces back to Neptune's migration early in the solar system's history. As Neptune moved outward through the disk of icy debris, its resonances swept across space like nets. Objects that encountered these resonances at the right moment were captured and carried along. Their orbits were reshaped, tilted, and elongated. Pluto was one of these captured objects. This process matters because it reverses the intuitive picture. Pluto did not form where it is now. Its orbit is not the result of peaceful, isolated evolution. It is the outcome of interaction with a more massive planet. Neptune's motion defined Pluto's fate, not the other way around. From the standpoint of planetary physics, this dependence is decisive. A planet is expected to shape the dynamical architecture of its surroundings. Pluto does not. Its orbit is an artifact of Neptune's influence. Remove Neptune, and Pluto's current path would not persist. Remove Pluto, and Neptune would not notice. Resonance also explains why Pluto's orbit is stable over immense timescales despite its unusual shape. Stability does not require simplicity, it requires balance. Resonant configurations can be extraordinarily robust, surviving perturbations that would destroy non-resonant orbits. This robustness is sometimes mistaken for evidence of planetary status. In reality, it demonstrates the power of gravitational control exerted by the dominant body. The mathematics of resonance makes this clear. When orbital periods form a ratio of small integers, the gravitational potential can be expanded into terms that reinforce rather than cancel. These terms create restoring forces that keep the system locked in place. For a massive planet, these forces extend far beyond its immediate vicinity. For a smaller body like Pluto, resonance is lifeline. There is also a subtle but important asymmetry in resonant systems. Energy and angular momentum are exchanged in ways that preserve the resonance while allowing other orbital elements to change. Pluto's eccentricity and inclination were likely increased during capture. These changes did not destabilize the orbit because resonance compensated. This kind of evolution is characteristic of objects that are shaped by the system rather than shaping it. If Pluto were a planet in the same sense as Earth or Neptune, this asymmetry would be reversed. Smaller bodies would resonate with Pluto. Pluto would define gaps, clusters, or stable regions around itself. Observations show no such effects. Pluto has moons, but they are dynamically insignificant beyond their immediate vicinity. The region around Pluto remains crowded with other bodies under Neptune's control. This is why resonance is such a powerful diagnostic tool in planetary physics. It reveals relationships of dominance and dependence that size alone cannot. An object can be spherical, geologically active and complex, yet still be dynamically subordinate. Motion exposes that subordination without ambiguity. It is also why the phrase, clearing the neighborhood, cannot be reduced to a casual description. Clearing is not about removing every object. It is about establishing gravitational authority. Resonant populations indicate the opposite. They signal regions where authority is shared or imposed from elsewhere. Pluto's orbit, viewed through this lens, becomes less mysterious and more instructive. It is not a failed planet wandering aimlessly. It is a record of Neptune's past and a tracer of the outer solar system's dynamical structure. Its resonance encodes information about migration, mass distribution, and long-term stability. The problem arises only when names are expected to override motion. Calling Pluto a planet suggests autonomy. Resonance reveals dependence. Physics sides with what can be measured. This does not mean Pluto is unimportant, quite the opposite. Because it has not dominated its region, Pluto has preserved features that dominant planets erased in their own neighborhoods. Its orbit is a fossil, its resonance is a signature. Through Pluto, scientists learn how the outer solar system evolved in ways that would otherwise be inaccessible. Resonance also prepares the ground for understanding objects even farther out. When Eris and similar bodies were discovered, their orbits showed related but distinct patterns. Some are resonant, some are scattered, some are detached, barely influenced even by Neptune. Each category reflects a different dynamical history, readable only through motion. Seen this way, Pluto's orbit is not an embarrassment to planetary science. It is a demonstration of why planetary science must remain anchored in dynamics. The solar system is not obligated to match human expectations of neatness. It reflects the cumulative outcome of gravitational interaction over billions of years. As attention continues to move outward, resonance remains a recurring theme. It explains why certain orbits persist, why others do not, and why classification based on behaviour becomes unavoidable. Pluto's path around the Sun is not just unusual, it is explanatory. It shows with quiet precision how gravity organises complexity without ever consulting a list. Pluto never fit quietly into the solar system because its motion carries the marks of a region where order was never fully established. Long before arguments about names or definitions, the physics was already clear in the shape and orientation of Pluto's orbit. Two properties in particular reveal this with remarkable consistency: inclination and eccentricity. These are not cosmetic details. They are measurements that describe how an object moves through space, and in a dynamical system, they often tell you more about an object's history and role than its size or composition ever could. Inclination describes how much an orbit is tilted relative to a reference plane. In the solar system, that reference is usually the plane in which Earth orbits the Sun, often called the ecliptic. Most major planets stay close to this plane. Their orbits deviate by only a few degrees. This is not coincidence. It reflects how the solar system formed. When the Sun was young, it was surrounded by a rotating disk of gas and dust. Collisions and interactions within that disk gradually flattened it, damping out large vertical motions. Objects that grew into planets formed within this disk and inherited its geometry. Pluto did not follow this pattern. Its orbit is tilted by more than 17 degrees relative to the ecliptic. That is an enormous deviation in planetary terms. Such a tilt cannot arise quietly. It requires strong gravitational interactions that disturb an object's original path. Inclination is, in this sense, a memory. It records the fact that Pluto experienced a dynamical environment very different from that of the inner planets. Eccentricity tells a related but distinct story. It measures how stretched an orbit is compared to a perfect circle. A value near zero indicates a nearly circular path. Larger values mean more elongated orbits. The major planets all have low eccentricities. Their distances from the Sun do not vary dramatically over the course of an orbit. This stability is another consequence of growth within a dense disk, where repeated interactions smoothed out extremes. Pluto's eccentricity is high. Its distance from the Sun varies so much that, for part of its orbit, it comes closer to the Sun than Neptune does. At other times, it is far beyond Neptune's reach. This elongated path again signals a history of disturbance, rather than quiet accumulation. In a dynamically calm environment, such an orbit would be unlikely to survive. Something must be maintaining it. Inclination and eccentricity together form a dynamical fingerprint. High values for both strongly suggest that an object did not grow into dominance within a settled disk. Instead, it points towards scattering, resonance capture, or long-term gravitational stirring. Pluto shows all three signatures. In planetary physics, this matters because dominant planets tend to erase such fingerprints in their own orbits. As they grow, they interact with surrounding material. These interactions exchange energy and angular momentum in ways that reduce eccentricity and inclination. The result is a near-circular, near-planar orbit. This is not a rule imposed by definition. It is an outcome of gravitational evolution. Pluto never experienced this smoothing process because it never became dominant. Its mass was too small, and its environment too sparse. Instead of calming its surroundings, Pluto was shaped by them. Its orbit reflects the combined influence of larger bodies, particularly Neptune, and the chaotic conditions of the outer solar system during its early history. This distinction is crucial. Inclination and eccentricity are not merely descriptors, they are indicators of power. A body that controls its region tends to impose order. A body that lacks that control tends to carry scars of disorder. Pluto's orbit is scarred in precisely this way. When astronomers first measured Pluto's orbit accurately, these features were already apparent. Even before resonance was understood in detail, Pluto stood out. It did not align with expectations for a planet formed in the same way as the others. At the time, however, there was little context. Pluto seemed alone. That context changed as surveys improved. Astronomers began finding other objects beyond Neptune with similarly tilted and elongated orbits. Some were smaller than Pluto, others were comparable. None showed the orderly behavior characteristic of dominant planets. Together, they formed a population rather than an exception. This population resides primarily in the region now known as the Kuiper Belt, but it is not uniform. Some objects occupy resonant orbits controlled by Neptune. Others have been scattered outward onto extreme paths. Some are detached, barely interacting with the known planets at all. What unites many of them is a lack of orbital neatness. High inclinations and eccentricities are common. From a dynamical standpoint, this makes sense. Beyond Neptune, the protoplanetary disk was thinner and less massive. Growth was slower. Interactions with the migrating giant planets stirred the region repeatedly. Objects were scattered, trapped, released, and scattered again. There was no extended period of calm during which a single body could grow large enough to dominate and impose order. Pluto's orbit fits perfectly into this picture. Its inclination and eccentricity are not anomalies, they're expected outcomes. The problem was never that Pluto behaved strangely. The problem was that it was treated as though it should behave like something it never was. Planetary physics does not treat such discrepancies as inconveniences, it treats them as data. When an object does not fit a category, the category is questioned. This is not disrespect for tradition, it is fidelity to evidence. Inclination also affects long-term stability in subtle ways. Highly inclined orbits experience different gravitational perturbations than low inclination ones. The geometry of encounters changes, resonances shift. In some cases, inclination can even enhance stability by reducing the likelihood of close approaches. Pluto's combination of inclination, eccentricity, and resonance produces a configuration that is stable, but clearly sculpted by external forces. This stability is sometimes misunderstood as evidence of planetary status. After all, Pluto's orbit is not chaotic, it has persisted for billions of years. But stability alone does not imply dominance. A leaf can float stably in an eddy without controlling the river. Pluto's orbit is stable because it is protected, not because it is powerful. Another important point is that inclination and eccentricity influence how an object interacts with its surroundings. A highly eccentric orbit swoops through a wide range of distances from the Sun, exposing the object to varying gravitational environments. A highly inclined orbit intersects the plane of the solar system at steep angles. These factors reduce the likelihood of sustained interactions with nearby bodies. In effect, such orbits isolate the object rather than centralize it. Dominant planets, by contrast, maintain orbits that maximize interaction within their zone. Their nearly circular, low inclination paths allow them to repeatedly encounter and influence nearby material. This repeated interaction is how clearing occurs. Pluto's orbit does the opposite. It minimizes encounters. It avoids competition. It survives by staying out of the way. This behavior is not accidental. It is enforced by resonance and by the absence of sufficient mass to alter the situation. Pluto cannot circularize its orbit because there is not enough material left to exchange energy with. It cannot flatten its inclination because it lacks the gravitational reach to do so. Its current path is effectively frozen. a snapshot of an earlier, more chaotic era. In this sense, Pluto is valuable precisely because it never fit quietly. Its orbit preserves information that planets erased. By studying its inclination and eccentricity, scientists infer the timing and nature of Neptune's migration, the mass distribution of the outer disk, and the processes that shape the Kuiper Belt. Pluto is not a misfit, it is a record. This is why planetary physics cares deeply about these orbital parameters. They are not abstract numbers, they are encoded history. They tell you whether an object grew up in peace or survived upheaval. They tell you whether it shaped its environment or was shaped by it. When Eris and other distant objects were later discovered, their orbits reinforced this understanding. Many showed even more extreme inclinations and eccentricities. Some orbit nearly perpendicular to the ecliptic. Some travel so far out that their orbital periods stretch into tens of thousands of years. None exhibit the orderly signatures of planetary dominance. By that point, the conclusion was no longer controversial within the physics. Pluto never fit quietly because it was never meant to. It belongs to a different dynamical class, one defined by shared behaviour rather than singular importance. The fact that this behaviour only became obvious once motion was prioritised over naming is not a failure of science. It is evidence of progress. As attention continues to move outward, inclination and eccentricity remain central tools. They help sort populations, reconstruct histories, and identify the limits of planetary influence. The solar system, viewed this way, is not a hierarchy imposed by labels, but a structure revealed by motion. Mass is the quiet authority in the solar system. It does not announce itself with brightness or spectacle, but through influence. In planetary physics, mass determines how strongly an object bends space around it, how effectively it alters the paths of others, and whether it merely exists within a region or actively reshapes it. When gravity becomes the governing language, mass becomes the grammar. Without enough of it, an object may survive, even endure for billions of years, but it will not rule. Gravity is not selective. Every object with mass exerts it. A grain of dust pulls on the sun just as the sun pulls on the grain of dust. The difference is not in kind, but in degree. The sun's mass is so overwhelming that the gravitational influence of smaller bodies becomes negligible by comparison. This imbalance sets the hierarchy of the solar system. Planets occupy their positions not because they were assigned them, but because their mass allowed them to impose order where smaller bodies could not. In physics, the strength of gravity depends on two things: mass and distance. Double the mass, and the gravitational pull doubles. Double the distance, and the pull drops by a factor of 4. This simple relationship governs everything from falling apples to planetary motion. It also explains why dominance is local. A planet's ability to shape space nearby diminishes with distance, but close to the planet its influence can be profound. This local dominance is the key to understanding planetary status. A planet is not defined by how impressive it looks or how complex its surface may be. It is defined by whether its gravity has reorganized the region around its orbit. Has it removed competitors? Has it scattered smaller bodies? Has it forced remaining objects into stable configurations where they no longer challenge its control? These outcomes are measurable consequences of mass acting over time. Consider Earth. Earth is not especially massive compared to the gas giants, but within its orbital zone it is dominant. There are no other Earth-sized bodies sharing its path. The reason is simple. During formation, Earth grew large enough to accrete nearby material and gravitationally scatter what it could not absorb. Over time, the region cleared. What remains are small asteroids, many of which are trapped in resonances or have orbits that avoid close encounters. Earth's mass was sufficient to finish the job. Now consider Pluto. Pluto's mass is tiny by planetary standards. It is less than 1/5 the mass of Earth's moon. Its gravitational reach is limited. While it can hold on to a few small moons, its influence does not extend far beyond that immediate system. It cannot scatter nearby bodies efficiently. It cannot clear its orbital zone. It cannot impose order on the surrounding population. Gravity tells this story without ambiguity. The ability to shape space nearby is not a vague concept. It can be quantified. One useful measure is the ratio between the mass of an object and the combined mass of other objects sharing its orbital region. For Earth, this ratio is enormous. Earth outweighs all other material in its zone by many orders of magnitude. For Pluto, the ratio is small. This is just one member of a population of comparable bodies. Another way to quantify dominance is through gravitational scattering efficiency. Massive planets alter the orbits of nearby objects through repeated encounters. Over time, these encounters either eject objects from the region, send them inward or outward, or cause collisions. The timescale over which this happens depends on mass. Large planets clear quickly. Small bodies do not. Jupiter is the extreme example. Its mass is more than twice that of all other planets combined. Its gravity shapes regions far from its orbit. It stabilizes Trojan asteroids, clears gaps in the asteroid belt, and deflects comets. Remove Jupiter, and the architecture of the solar system would change dramatically. Remove Pluto, and the system would be essentially unchanged. This contrast is not a judgment of importance. It is a statement of dynamical influence. Pluto is scientifically valuable because it preserves information about the outer solar system, but influence and importance are not the same thing in physics. A thermometer is important, but it does not control the temperature. The relationship between mass and orbital control also explains why size alone is misleading. An object can be physically large but still dynamically weak if its mass is low relative to its environment. Conversely, a smaller object can be dynamically powerful if it dominates a sparse region. This is why roundness, which depends on internal gravity overcoming material strength, is not sufficient to define a planet. Internal structure and external influence are different questions. In the outer solar system, this distinction becomes critical. Beyond Neptune, the available mass is spread thinly across a vast volume. Objects grow slowly. None reach the threshold required to dominate completely. Even the largest bodies there, including Pluto and Eris, remain gravitationally modest. Their ability to shape space nearby is limited to their immediate vicinity. This limitation shows up clearly in orbital simulations. When physicists model the outer solar system, they include the gravitational influence of the major planets. The contributions of smaller bodies are often negligible. Their presence does not significantly alter the long-term evolution of the system. This is not because they do nothing, but because their mass is insufficient to compete. Mass also determines whether an object can resist being shaped by others. A dominant planet not only shapes its surroundings, but maintains its own orbit against perturbations. Smaller bodies are more easily nudged. Over time, these nudges accumulate. Orbits tilt, stretch, and shift. Pluto's orbit bears the marks of this process. It is stable but not self-determined. This dependence becomes especially clear when considering resonance. Pluto's resonance with Neptune exists because Neptune's mass is large enough to enforce it. Pluto cannot impose a comparable resonance on Neptune. The exchange of energy and angular momentum is asymmetric. One body sets the terms, the other adapts. From a physics perspective, this asymmetry is decisive. A planet is expected to be the source of such constraints, not merely their subject. This is why mass thresholds matter. Without sufficient mass, an object cannot graduate from participant to architect. It is also why planetary classification does not scale smoothly. There is no gentle transition from non-planet to planet based on size alone. The transition occurs when mass crosses a threshold relative to the local environment. Below that threshold, objects coexist. Above it, one object dominates. The threshold depends on distance from the star, local density, and formation history. But the principle remains consistent. In the inner solar system, Where material was dense and orbital periods were short, this threshold was easier to reach. In the outer solar system, where material was sparse and interactions were slower, it was not. Physics predicts this outcome. It does not require special cases. Understanding mass in this relational way also clarifies why discovering Eris was so important. Eris is slightly more massive than Pluto, but not dramatically so. Its discovery did not introduce a new class of dominant bodies. It revealed that Pluto was not unique. Both objects occupy a regime where mass is insufficient to control the surrounding space. They are peers, not outliers. This realization forced a choice. Either accept that planetary status applies to a wide population of dynamically similar objects, or refine the definition to reflect gravitational influence. Physics favors the latter because it preserves explanatory power. Categories that lump together objects with radically different dynamical roles become useless. There is also a temporal aspect to mass and influence. Gravity works slowly at great distances. Clearing a region at Pluto's distance from the Sun would take far longer than the age of the solar system, even for a body somewhat more massive than Pluto. This means that dominance is not only about mass but about timescale. A planet must be capable of shaping its region within the lifetime of the system. Pluto cannot. This timescale argument removes ambiguity. Even if Pluto were left alone for billions more years, its mass is too small to clear its zone. The population would persist. Its gravitational influence would remain local. Physics does not predict a different outcome. The ability to shape space nearby also includes shaping trajectories of incoming objects. Massive planets act as gatekeepers. They redirect comets, capture moons, and influence impact rates on inner worlds. Smaller bodies lack this reach. Pluto does not shepherd comets or protect inner regions. Its gravitational sphere of influence is tiny on a solar system scale. This does not diminish Pluto's intrinsic interest. It has a complex surface, a tenuous atmosphere, and a fascinating moon system. But none of these features alter its gravitational role. In planetary physics, role matters more than character. As this understanding settles, the distinction between planets and other bodies becomes clearer. Planets are defined by what they do, not by what they resemble. They shape, clear, scatter, and organize. Objects like Pluto and Eris exist within that organization, rather than directing it. The phrase, clearing the neighborhood, sounds casual, almost conversational, and that casual tone is part of the problem. Outside of physics, it can sound like a vague suggestion, as if a planet is expected to tidy up space the way someone might straighten a room. In planetary dynamics, however, the idea has nothing to do with neatness, and everything to do with long-term gravitational control. It is a precise concept rooted in mass, timescale, and orbital behavior, and once those elements are spelled out carefully, the meaning becomes far less subjective than it is often portrayed. In physics, a neighborhood is not a region defined by lines drawn on a diagram. It is a region defined by interaction. Specifically, it refers to the range of orbits where objects experience repeated, significant gravitational encounters with a given body over the lifetime of the system. If two objects share nearby orbital paths around the Sun, they will eventually influence each other unless something prevents that interaction. Over millions or billions of years, those interactions determine whether one object becomes dominant or whether many objects continue to coexist. Clearing does not mean removing every last particle. Space is never empty. Even near Earth, dust, meteoroids, and small asteroids persist. What clearing means, in physical terms, is eliminating other bodies of comparable size from that interaction zone. A planet has cleared its neighborhood when it overwhelmingly outweighs all other objects that can meaningfully compete with it gravitationally along its orbit. This competition is not hypothetical. Early in the solar system's history, every orbital zone was crowded. Planetesimals collided, merged, fragmented, and scattered. Some grew larger, others were removed. The outcome depended on gravitational strength and time. A body that became massive early gained an advantage. Its gravity allowed it to accrete material faster, scatter rivals more efficiently, and establish a feedback loop that reinforced its dominance. From a dynamical perspective, clearing happens through a small number of physical processes. One is accretion. When two objects collide at low relative speed, they merge. The larger body grows, and the smaller one ceases to exist as an independent competitor. Another process is scattering. Gravitational encounters can alter an object's orbit, sending it inward toward the Sun, outward to distant regions, or onto a highly inclined or eccentric path that removes it from regular interaction. A third process is resonant trapping, where objects are forced into stable configurations that prevent close encounters but also prevent further growth. All three processes depend on mass. A body with insufficient mass cannot accrete efficiently because collisions are rare and low energy. It cannot scatter rivals effectively because its gravitational pull is weak. It cannot impose resonances that restructure the region. Such a body remains one member of a population rather than emerging as a controller of that population. Physics makes this quantitative. One commonly used measure of clearing ability is the planet's mass relative to the total mass of other objects in its orbital zone. For Earth, this ratio is enormous. Earth outweighs all remaining material near its orbit by many orders of magnitude. The same is true for the other major planets. Even Mars, small by planetary standards, dominates its region dynamically. For Pluto, the situation is very different. Pluto shares its orbital zone with a large number of other bodies in the Kuiper Belt. Some are smaller, some are comparable. Collectively, they represent a population that Pluto has not removed, reorganized, or dominated. Pluto's mass is not overwhelmingly larger than the mass of its neighbours. As a result, gravitational competition persists rather than resolving. Another way to frame clearing is through timescale. Clearing is not instantaneous. It takes time for repeated interactions to accumulate into decisive outcomes. A planet must be able to clear its neighbourhood within the age of the solar system, given its distance from the Sun and the density of material in its region. This constraint is critical. Far from the Sun, orbital periods are long. Objects move slowly. Encounters are infrequent. Even a moderately massive body may take longer than the age of the solar system to clear its zone at large distances. This is why dominance is harder to achieve in the outer solar system. It is not merely that objects that are smaller. The environment itself resists rapid clearing. Physics accounts for this by considering gravitational scattering timescales. These depend on mass, orbital velocity, and encounter frequency. When these factors are combined, it becomes clear that Pluto could not clear its neighbourhood even if it were left undisturbed for billions more years. Its mass is too small, its encounters too weak, and its region too vast. This removes the idea of clearing from the realm of opinion. It becomes a prediction. Given Pluto's mass and orbit, physics predicts persistent coexistence, not dominance. Observations confirm this prediction. The Kuiper Belt remains populated. Pluto remains one object among many. Importantly, clearing does not require perfection. Jupiter has not removed every asteroid from its vicinity. Neptune has not eliminated all distant icy bodies. What these planets have done is establish a clear hierarchy. They dominate the mass budget of their zones. They control the structure of nearby populations. Smaller bodies exist, but they exist on the planet's terms. This distinction is often missed in casual discussions. Clearing is about relative influence, not absolute emptiness. A planet that dominates its zone may still host debris, moons, or resonant populations. What it does not host is rivals. Resonant populations, in fact, are evidence of clearing rather than failure to clear. When Neptune traps objects into resonances, it prevents them from becoming competitors. They are locked into specific orbital relationships that maintain Neptune's dominance. The presence of resonant objects shows that the planet's gravity has reorganized the region, not that it has failed. By contrast, Pluto does not trap a significant population into resonances of its own. Its gravity is too weak to enforce such structure. It does not carve gaps. It does not shepherd distant objects. It follows patterns imposed by others. This is why the phrase "clearing the neighbourhood" cannot be reduced to size or shape. An object can be round and geologically complex without being dynamically dominant. Internal gravity shapes an object's form. External gravity shapes its environment. These are separate regimes governed by the same force, but applied at different scales. Another important aspect of clearing is orbital crossing. In a fully cleared neighbourhood, the dominant planet's orbit does not intersect with those of other comparable bodies. Crossing orbits would lead to repeated encounters, instability, and eventual resolution. The fact that Pluto's orbit crosses Neptune's is itself a signal. It tells us that Pluto is not the dominant body in that region. Neptune is. The stability of this crossing is sometimes cited as evidence against the clearing criterion, but physics shows the opposite. The crossing is stable precisely because Neptune dominates. Pluto survives by staying in resonance, not by asserting control. If Pluto were dominant, Neptune would not tolerate such crossings. Clearing also connects directly to formation. Planets form by growing until competition ends. Once a body has removed or neutralized rivals, growth slows dramatically. The planet enters a mature phase. Regions where competition never ended remain populated. Pluto's region is one of these. This population aspect is critical. Physics recognizes families and distributions. When many objects share similar dynamical characteristics, they are treated as a class. Pluto belongs to such a class. It is not an isolated endpoint of growth. It is a survivor among peers. The decision to formalize clearing as a criterion was therefore not arbitrary. It was an attempt to align terminology with physical reality. Without it, the word planet would apply equally to bodies that dominate their regions and bodies that do not. That equivalence would erase meaningful distinctions in behaviour. In scientific classification, such erasure is a problem. Categories are tools. They must group objects that behave similarly and separate those that do not. When a category becomes too broad, it loses predictive value. Clearing restores that value by anchoring classification to dynamics. This does not mean that clearing is the only thing that matters. It is one criterion among several, but it is the criterion that connects directly to system-wide behaviour. Orbiting the Sun is common. Being round is common. Dominating a region is rare. Physics prioritizes the rare property because it explains structure. Clearing also scales naturally to other systems. When astronomers study exoplanetary systems, they apply the same logic. They look for bodies that dominate their orbits, shape debris disks, and establish long-term stability. The physics does not change just because the star does. This universality is another reason the criterion matters. A definition that works only for one system is not a physical definition. Clearing works wherever gravity governs. It is worth noting that clearing is not a moral judgment. It does not imply superiority or worth. It describes a role. A hammer is not better than a thermometer, but they are not interchangeable. Calling both by the same name would be confusing. Pluto's failure to clear its neighbourhood is not a flaw. It is a fact about its mass, location, and history. That fact makes Pluto valuable as a window into the early solar system. Dominant planets erase history. Subordinate ones preserve it. When this is understood, the controversy surrounding the term begins to dissolve. The criterion does not diminish Pluto, it clarifies it. It explains why Pluto behaves the way it does, and why its orbit looks the way it does. As this clarification settles in, the broader picture becomes easier to follow. Clearing is not a rule invented to exclude. It is a description of an outcome that gravity produces naturally when conditions allow. Where those conditions are not met, populations persist and different categories become useful. Orbital dominance is not a metaphor. In planetary physics, it is a measurable outcome of equations that describe how mass controls motion over time. When scientists talk about one body dominating an orbital region, they are not expressing preference or hierarchy in a cultural sense. They are describing a situation where the mathematics of gravity leaves little doubt about who controls whom. This control is subtle, cumulative, and indifferent to how objects are named. It emerges from repeated interactions governed by well-understood laws. At the heart of orbital dominance lies Newtonian gravity. Every object attracts every other object, and the force between them depends on mass and distance. In a simple two-body system, the result is clean and predictable. Add a third body, and the system becomes more complex. Add thousands or millions, and long-term behaviour can only be understood statistically and numerically. The solar system exists in this latter regime. Dominance is not about one dramatic interaction. It is about the aggregate effect of countless small ones. To make this concrete, physicists often begin by asking a simple question. If two objects share nearby or overlapping orbits around the Sun, what happens over long timescales? The answer depends almost entirely on their relative masses. When one object is much more massive than the other, gravitational encounters are asymmetric. The smaller body experiences large changes in its orbit. The larger body barely notices. This asymmetry is the foundation of control. Over time, repeated encounters allow the massive body to reshape the orbital distribution of smaller ones. It can scatter them inward, outward, or eject them entirely from the system. It can also trap them in resonances that prevent further competition. The smaller bodies cannot do the reverse. Their cumulative effect on the massive body averages out to almost nothing. Mathematically, this is described through perturbation theory. The orbit of a planet around the Sun is treated as the dominant motion, while interactions with other bodies are treated as perturbations. The size of those perturbations depends on mass ratios. When the mass ratio is extreme, perturbations act almost entirely in one direction. This is why planets remain stable while debris populations are reshaped. One way to express orbital dominance quantitatively is through a parameter known as the planetary discriminant. This value compares the mass of a body to the total mass of other objects that share its orbital zone. While the exact formulation can vary, the result is robust. For the 8 major planets, this value is extremely large. For bodies like Pluto, it is very small. There is a clear gap, not a smooth transition. This gap matters because it reflects a qualitative change in behaviour. Above a certain threshold, a body clears and controls. Below it, coexistence persists. The mathematics does not care where humans choose to draw the line. It simply shows that two regimes exist. Another mathematical tool used to study dominance is the Hill radius. This defines the region around a body where its gravity dominates over the tidal influence of the Sun. Inside this region, the body can retain moons and exert local control. Outside it, the Sun's gravity wins. Larger mass produces a larger Hill radius, expanding the zone of influence. All planets have Hill spheres large enough to host stable satellite systems. Pluto does as well, but its Hill sphere is tiny compared to planetary ones. More importantly, the Hill sphere alone does not guarantee orbital dominance. It defines local control, not regional authority. Clearing a neighbourhood requires influence far beyond the Hill sphere, through repeated encounters along shared orbital paths. Orbital dominance also depends on encounter velocity. Objects closer to the Sun move faster. Encounters are more energetic and more frequent. This allows planets in the inner solar system to clear their zones more efficiently, even if they are less massive than outer planets. Farther out, velocities are lower and encounters rarer. Mass must be much larger to achieve the same effect. This dependence on distance is why dominance is harder to achieve in the outer solar system. Even a body somewhat more massive than Pluto would struggle to clear its zone at that distance within the age of the solar system. The mathematics predicts this outcome without ambiguity. It is not that Pluto failed to clear its neighbourhood, it is that physics never allowed it to. Simulations make this especially clear. When physicists model the early solar system, They populate regions with many bodies and allow them to interact according to gravitational laws. Over time, dominant bodies emerge naturally where conditions permit. In other regions, populations persist. These simulations reproduce the present-day structure of the solar system with remarkable accuracy. No special rules are required. Control also manifests in angular momentum exchange. In gravitational encounters, angular momentum can be transferred between bodies. Massive planets act as reservoirs. They can absorb or supply angular momentum with little change to their own orbits while dramatically altering those of smaller bodies. This is another mathematical expression of dominance. The equations governing these exchanges depend explicitly on mass ratios. Resonances provide a related but distinct mathematical signature. When a massive body imposes a resonance, it constrains the phase space available to smaller objects. Certain orbits become forbidden, others become stable attractors. The dominant body effectively sculpts the distribution of possible motions. This sculpting is visible in asteroid belts, debris disks, and trans-Neptunian populations. By contrast, smaller bodies cannot carve such structure. They respond to resonances rather than creating them. Their motion is constrained by the dominant planets, not the other way around. This asymmetry is visible in frequency maps and stability diagrams generated by numerical analysis. The mathematics does not leave room for interpretation. Another important concept is chaotic diffusion. In regions where no single body dominates, small perturbations can accumulate in unpredictable ways. Orbits wander through phase space. Populations remain dynamically excited. Clearing does not occur because no object has sufficient mass to impose order. This behavior characterizes much of the Kuiper Belt. Orbital dominance suppresses chaos locally. By removing competitors and enforcing resonances, a planet reduces the degrees of freedom available to nearby bodies. The system becomes more predictable. This predictability is another mathematical marker of control. It is also worth noting that dominance is scale-dependent. A moon can dominate its immediate vicinity around a planet without being dominant in the solar system as a whole. Physics recognizes this nested hierarchy. Each level has its own controlling bodies. Confusion arises only when categories are applied across levels without regard for scale. This hierarchical structure is not arbitrary. It emerges naturally from the equations of motion. Mass and distance determine influence. Influence determines structure. Structure determines classification. Occupy a regime where their mass, and occupy a regime where their mass and location allow them to impose long-term order. Pluto and similar objects do not. This is not a close call. The numbers differ by orders of magnitude. It is sometimes argued that dominance is an evolving property, that Pluto might one day clear its neighbourhood. The mathematics answers this as well. Given Pluto's mass, orbital velocity and encounter rates, the timescale required exceeds the remaining lifetime of the Sun by many orders of magnitude. Control will never emerge. This predictive power is why physics relies on mathematics rather than intuition. Intuition struggles with vast timescales and weak forces. Equations handle them effortlessly. Orbital dominance also generalizes beyond our solar system. In exoplanetary systems, astronomers identify dominant planets by their effect on debris disks and smaller companions. The same mathematical criteria apply. Where dominance exists, structure emerges. Where it does not, populations persist. This universality reinforces confidence in the concept. It is not a rule invented for one controversial case. It is a reflection of how gravity behaves everywhere. When all of this is taken together, the phrase clearing the neighbourhood resolves into something precise. It describes a body whose mass and location place it in a regime where the mathematics of gravity predict long-term control over its orbital region. That control manifests as the removal, rearrangement or suppression of rivals. Pluto does not meet these conditions, neither does Eris. Their orbits, masses and environments place them firmly in the population regime. This conclusion follows directly from equations, not from votes or conventions. Understanding orbital dominance in this way removes the emotional charge from the discussion. The classification follows from the math. Gravity does not negotiate, and the equations do not compromise. As the analysis continues outward into regions where dominance becomes rare and populations flourish, these mathematical tools remain essential. They allow scientists to distinguish between control and coexistence, between architects and residents, without relying on tradition or familiarity. The Kuiper Belt is best understood not as a collection of exceptions, but as a population governed by shared gravitational circumstances. Once the solar system is viewed as a dynamical system, rather than a list of privileged objects, the Kuiper Belt stops looking like an afterthought and begins to look like exactly what physics predicts should exist at the outer edge of planetary influence. It is a region where gravity never resolved competition into dominance, and where coexistence became the stable outcome. From a distance, it is tempting to imagine the Kuiper Belt as a sparse ring of debris beyond Neptune. In reality, it is a vast three-dimensional region populated by countless icy bodies moving on a wide variety of orbits. Some follow relatively calm, low eccentricity paths. Others are tilted steeply. Many are stretched into long ellipses. This diversity is not noise. It is the defining feature of a gravitational population. In physics, a population emerges when no single object has enough mass to impose order on the rest. Instead of one body shaping the region retains many bodies of comparable dynamical status. Their interactions are weak, infrequent, and largely unresolved. The system does not converge toward hierarchy. It remains distributed. The Kuiper Belt occupies such a regime. Beyond Neptune, the surface density of material in the early solar system dropped sharply. There simply was not enough mass concentrated in that region for a planet to grow large enough to dominate before the gas disk dispersed. Growth stalled. Objects reached sizes of hundreds or even thousands of kilometers, but none crossed the threshold into regional control. This outcome was not an accident. It was the natural result of formation physics. Accretion depends on collision frequency. Collision frequency depends on number density and orbital velocity. Far from the Sun, orbital speeds are low and distances between objects are large. Collisions are rare. Growth is slow. Before any single body could take over, the conditions that enabled growth disappeared. What remained was a population of survivors. In a gravitational population, individual objects matter less than the statistical properties of the group. Physicists therefore describe the Kuiper Belt in terms of distributions rather than exemplars. They measure inclination distributions, eccentricity distributions, size distributions, and resonance fractions. These quantities reveal far more about the system than focusing on any one object ever could. One of the most telling features of the Kuiper Belt is its division into subpopulations. There are resonant objects trapped by Neptune's gravity. There are classical objects with relatively stable, non-resonant orbits. There are scattered objects with highly eccentric paths shaped by past encounters. There are detached objects that barely interact with Neptune at all. Each group reflects a different gravitational history. None of these groups is defined by a single dominant body within the belt itself. Instead, their structure is imposed from outside, primarily by Neptune. This is a key point. The Kuiper Belt is shaped, but not ruled. Its architecture reflects influence without control. In planetary physics, this distinction is crucial. A controlled region shows signs of clearing, hierarchy, and imposed order. A shaped region shows signs of external perturbation layered onto internal coexistence. The Kuiper Belt shows the latter. This is why objects like Pluto and Eris fit naturally into the Kuiper Belt framework. Their orbits, masses, and interactions are consistent with membership in a gravitational population. They do not stand apart from it. They exemplify it. From the standpoint of dynamics, Pluto is not in the Kuiper Belt as a planet visiting a neighbourhood. It is of the Kuiper Belt. Its resonance with Neptune, its inclination, and its eccentricity are all typical of objects whose histories were shaped by migration and scattering rather than by autonomous growth. Population behaviour also explains why the Kuiper Belt remains dynamically excited. Many objects retain high inclinations and eccentricities. There has been no dominant body to damp these motions. Without repeated strong encounters with a massive planet inside the belt, there is no mechanism to smooth out orbital extremes. The belt remains stirred. This stirred state persists because gravitational interactions among belt objects are too weak to resolve it. Their masses are small relative to their separations. Mutual perturbations are negligible on solar system timescales. Chaos exists, but it is slow. Evolution continues, but it does not converge. In this sense, the Kuiper Belt resembles other population-dominated systems in astrophysics. Star clusters, for example, behave differently depending on whether a massive central object dominates. Galaxies with supermassive black holes show different dynamics than those without. In every case, dominance simplifies structure. Its absence preserves complexity. The Kuiper Belt preserves complexity. Another defining feature of a gravitational population is that its boundaries are fuzzy. There is no sharp edge where the belt begins or ends. Objects gradually transition into scattered disk populations and detached orbits. This gradual change is exactly what physics predicts when no single body defines a boundary. Lists require edges. Systems do not. The recognition of the Kuiper Belt as a population resolved several long-standing puzzles. Why were so many distant objects found with similar sizes and compositions? Why did their orbits resist simple categorization? Why did adding more discoveries make the system feel less orderly rather than more? The answer was that order was never the right expectation. Once this realization took hold, the role of classification shifted. The question stopped being how many planets the solar system has and became how many dynamical regimes it contains. Interplanetary dominance is one regime. Gas giant dominance with resonant sculpting is another. Population-dominated outskirts form yet another. Within that outer regime, objects are classified by behaviour, not by prestige. A dwarf planet is not a lesser planet. It is a member of a different gravitational class. The term describes how it interacts, not how it compares emotionally. This population view also explains why adding Eris did not create a new crisis. Eris did not introduce a new behaviour. It reinforced an existing pattern. Its mass and orbit placed it squarely among other large Kuiper Belt objects. The system made sense once objects were compared to each other, rather than to outdated expectations. Physics prefers populations because populations allow prediction. If you know the statistical properties of the Kuiper Belt, you can predict impact rates, migration histories, and even the likelihood of similar structures around other stars. Individual names do not offer that power. This perspective also changes how exploration is valued. Sending a spacecraft to Pluto was not important because Pluto was a planet. It was important because Pluto is a representative of a major solar system population. Studying it revealed information about countless other objects that will never be visited directly. In that sense, Pluto's scientific importance increased as its classification became more precise. It stopped being an oddity and became a key data point. The Kuiper Belt also serves as a reminder that the solar system did not finish forming everywhere at once. Formation is local. Outcomes depend on conditions. Where mass was abundant and time was short, planets formed. Where mass was sparse and time ran out, populations remained. This is not a failure of formation. It is its full expression. Gravitational populations are not incomplete systems waiting for resolution. They are stable endpoints given their constraints. The Kuiper Belt will not one day condense into a new planet. The Sun will evolve before that could happen. The population is here to stay. This permanence matters. It means that classification based on current dynamics is not temporary. It reflects long-term reality. Pluto and Eris are not planets in waiting. They are what they will always be. When planetary physics embraces populations, it gains explanatory coherence. The solar system stops looking like a story with an awkward ending and starts looking like a spectrum of outcomes produced by the same laws acting under different conditions, and as the focus continues outward, the Kuiper Belt remains the context in which every distant object must be understood, a gravitational society without a ruler, shaped from afar, stable in its complexity, and quietly defining the limits of planetary authority. Eris entered the equations quietly, not as a dramatic interruption, but as an unavoidable term that refused to cancel out. There was no single night when the solar system suddenly changed. No orbit shifted, no planet moved. What changed was the accounting. Once Eris was measured carefully, once its mass, distance and motion were placed into the same mathematical framework, already used for everything else, the existing picture could no longer balance the way it once had. Eris was discovered in the early years of the 21st century, detected not by chance but by systematic surveys of the outer solar system. Astronomers were no longer stumbling upon distant objects accidentally. They were scanning deliberately, mapping large areas of sky, comparing images taken months apart, and identifying faint points of light that moved just enough to betray their membership in the solar system rather than the background of stars. Eris appeared as one such moving point, slow and distant, barely distinguishable from noise until repeated observations confirmed its path. From the beginning, Eris was different not because it behaved strangely, but because it behaved familiarly. Its orbit placed it far beyond Neptune for most of its long journey around the Sun. It was highly inclined, tilted steeply relative to the plane of the planets. Its eccentricity was extreme, carrying it from a distant aphelion far into the scattered outskirts of the solar system to a perihelion still well beyond Neptune's orbit. In dynamical terms, Eris immediately belonged to the same broad regime as Pluto and other large Kuiper Belt objects. At first, the most striking feature of Eris was not its orbit, but its brightness. Once distance was accounted for, Eris appeared to be at least as large as Pluto, and possibly larger. Size estimates improved as better observations became available, and eventually its mass could be determined through the motion of its moon, dysnomia. This is where Eris stopped being merely interesting and became decisive. Mass is not negotiable. It enters directly into the equations of motion. When Eris's mass was calculated, it became clear that Eris was slightly more massive than Pluto. The difference was not dramatic, but it was unambiguous. In every physically meaningful sense that mattered for classification, Eris matched or exceeded Pluto. This was the moment when the equations refused to cooperate with tradition. If Pluto was considered a planet, then Eris had to be one as well. There was no physical basis for excluding it. Their masses were comparable. Their orbits placed them in the same dynamical environment. Their ability to influence their surroundings was similarly limited. Treating one as fundamentally different from the other would require a non-physical justification. Planetary physics does not allow such a symmetry. When two objects occupy the same dynamical regime, they belong to the same class. This is not a matter of preference, it is a requirement for consistency. The problem was not that Eris challenged Pluto. The problem was that Pluto had already been quietly challenging the definition of a planet for decades, and Eris made that challenge impossible to ignore. Pluto could be treated as a historical exception, only as long as it appeared unique. Eris demonstrated that it was not. Once Eris entered the equations, the solar system could no longer be described as having a small closed set of planets, followed by a handful of odd leftovers. Instead, it became clear that beyond Neptune lay a population containing multiple bodies comparable to Pluto in size and mass, all sharing similar dynamical characteristics. Eris was simply the first of these to be massive enough to force the issue. From a mathematical standpoint, nothing about Eris required a new theory. The same gravitational equations applied. The same criteria for dominance, clearing and control yielded the same answers. Eris did not clear its neighbourhood. It did not dominate its orbital region. It was shaped by Neptune's migration and by long-term gravitational scattering. Its motion placed it firmly within the population regime. The discomfort arose not from the physics, but from the mismatch between physics and language. Before Eris, it was possible, though increasingly strained, to maintain a planet list that included Pluto as a sentimental endpoint. After Eris, that list could not expand without losing coherence. Each additional discovery of a Pluto-like object would demand inclusion. The solar system would swell to dozens of planets, then hundreds, as surveys improved. The word planet would no longer describe a distinct dynamical role. It would describe little more than size. Physics does not reward such dilution. When a term becomes too broad, it stops explaining anything. Eris made that outcome unavoidable unless the definition was refined. What matters here is that Eris did not introduce ambiguity. It removed it. By matching Pluto so closely in mass and behaviour, Eris eliminated the possibility that Pluto occupied a unique category. Either both were planets, or neither was. The equations did not permit a third option. The orbit of Eris reinforced this conclusion. Eris is not merely distant. It is dynamically detached for much of its orbit, interacting weakly with Neptune and spending long stretches far from the region of strongest planetary influence. This behaviour places it among the scattered and detached populations, not among dominant bodies. Its path through space reflects a history of gravitational perturbation rather than autonomous growth. This history is written into its orbital elements. High inclination indicates past scattering. Extreme eccentricity indicates encounters or resonant interactions that altered its energy. Long orbital periods indicate formation in a sparse environment where accretion was slow. Each of these properties aligns with the population model of the outer solar system. When Eris was incorporated into numerical simulations, nothing broke. The models that explained Pluto also explained Eris. The same migration scenarios for Neptune produced objects like Eris naturally. The same mass distribution predictions held. This internal consistency is one of the strongest indicators that the underlying framework is correct. What broke instead was the idea that Pluto could remain classified based on historical inertia rather than physical behaviour. In that sense, Eris did not demote Pluto. Eris clarified Pluto. This distinction matters because it reframes the debate entirely. The change in classification was not a response to Eris as an inconvenience. It was a response to Eris as evidence. Physics responded the only way it knows how, by adjusting definitions to match observations. The fact that Eris is slightly more massive than Pluto also undermines another common intuition, that planetary status should track size in a simple way. If Pluto were a planet, then Eris would be a planet too, despite being farther away, more inclined and more detached. The solar system would then include planets that do not dominate their regions, do not define clear orbital zones, and do not shape the overall architecture. Such a classification would flatten meaningful differences. It would place Jupiter and Eris under the same label despite their radically different roles. From a physical standpoint, this is unacceptable. Jupiter shapes the entire solar system. Eris shapes almost nothing beyond itself. Eris's discovery also highlighted the predictive power of population thinking. Once Pluto was recognized as part of a broader class, the existence of Eris became expected rather than surprising. Surveys predicted that objects of comparable size should exist. Eris confirmed that prediction. This is an important point. Science values predictions that come true more than surprises. Eris was valuable not because it was shocking, but because it fit where it should. It validated the idea that the Kuiper Belt contained large bodies formed through the same processes that produce Pluto. The equations did not need Eris to be larger than Pluto to make this point. Even if Eris had been slightly smaller, its existence would still have forced reconsideration. That it turned out to be slightly more massive simply removed any remaining ambiguity. Once Eris entered formal discussions, the question shifted from discovery to definition. How should planetary status be defined in a way that remains consistent as new objects are found? The answer could not depend on discovery order or public familiarity. It had to depend on physical criteria that would scale. Eris tested that scalability. If a definition could not accommodate Eris without contradiction, then the definition was flawed. Physics demanded revision, not exception. This is why the eventual decision did not hinge on Eris alone, but Eris was the catalyst. It forced astronomers to confront the fact that the solar system does not end neatly. It fades into a population regime where dominance is rare and coexistence is the norm. Eris also made clear that the solar system is not finished revealing itself. If Eris exists, then others like it likely do as well. Some may be smaller, some may be larger, some may follow even more extreme orbits. Classification must be robust enough to handle all of them. The equations that describe gravitational dynamics already are. They do not care how many objects are added. They respond the same way every time. Mass determines influence. Influence determines role. Eris's role is unambiguous. It does not dominate, it does not clear, it does not control, it persists. That persistence is not a failure. It is the defining feature of a gravitational population. As Eris settled into the catalogue, the solar system itself did not change. What changed was the willingness to let equations override habit. That willingness is what allowed planetary science to move forward without accumulating contradictions. Eris, in that sense, is not an interloper. It is a correction term. It ensures that the sum of our understanding balances. Eris forced a redefinition, not an addition, because physics does not expand categories when evidence demands refinement. When a system becomes more complex under observation, the scientific response is not to stretch existing labels until they lose meaning, but to sharpen those labels so they continue to describe reality accurately. Eris did not arrive as a candidate waiting to be promoted. It arrived as a constraint, a boundary condition that exposed a mismatch between how the solar system was being described and how it actually behaves. Before Eris, it was still possible, though increasingly uncomfortable, to treat Pluto as a singular case. Pluto could be spoken of as an odd planet, a small one, a distant one, but still a planet. This approach relied on isolation. As long as Pluto appeared to stand alone at the edge of the solar system, its unusual properties could be tolerated as quirks rather than contradictions. Physics allows quirks only temporarily. Once patterns emerge, quirks become data. Eris erased Pluto's isolation. From the moment Eris's orbit and mass were known, it became clear that Pluto was no longer unique in any physically meaningful sense. Both objects occupy similar regions of space. Both move on highly inclined eccentric orbits. Both are members of the Kuiper Belt population shaped by Neptune's migration. Both lack the mass required to dominate their surroundings. In every dynamical category that matters, they belong together. This created a logical fork. Either Pluto and Eris were both planets, or neither was. Adding Eris as an additional planet without revisiting the definition would have solved nothing. It would have deepened the inconsistency. If Eris were added as a planet under the old logic, then the reason Pluto was considered a planet would no longer be sufficient. Pluto had been a planet largely because it was discovered early, appeared large enough, and fit comfortably into a simple list. Eris met all those criteria except discovery order. Physics cannot privilege chronology. The universe does not care which object humans noticed first. Adding Eris would also have committed planetary science to a runaway expansion. Eris is not the only large Kuiper Belt object. It is one of the largest known, but it is not alone. Objects such as Haumea and Makemake follow similar dynamical rules, and ongoing surveys continue to reveal more distant bodies. Some may rival Pluto or Eris in size, some may exceed them. If size and roundness were sufficient for planetary status, then each new discovery would demand inclusion. At that point, the word planet would no longer describe a distinct physical role. It would describe a growing inventory of objects with widely different dynamical behaviours. Jupiter and Eris would share a label despite having almost nothing in common in terms of influence, formation or function. This is exactly the situation physics avoids. Scientific categories exist to compress information. A good category allows you to infer behaviour from membership. If something is called a planet, you should be able to make reasonable predictions about how it behaves dynamically. Adding Eris without redefining the category would destroy that predictive power. Redefinition, by contrast, restores it. By revisiting what planet should mean in physical terms, astronomers were able to preserve a category that reflects gravitational reality. A planet became defined not by appearance or tradition, but by dominance. This definition did not exclude Eris arbitrarily. It described why Eris behaves the way it does. This distinction is subtle but essential. Eris did not fail to qualify because it was distant, cold, or unfamiliar. It failed to qualify because it occupies a different dynamical regime. It shares space with many comparable bodies. It does not control that space. Its orbit is shaped by others rather than shaping them. The same is true of Pluto. Once this was acknowledged, the only coherent response was to redefine the category so that it matched behaviour rather than history. This is not an act of subtraction. It is an act of alignment. It is also important to understand that redefinition did not arise from Eris alone. Eris was the tipping point, but the underlying tension had been building for decades. Discoveries of Kuiper Belt objects in the 1990s had already revealed that Pluto was part of a broader population. Resonances, inclinations, and eccentricities all pointed in the same direction. Eris simply made the conclusion unavoidable. In physics, unavoidable conclusions are not resisted indefinitely. They may be debated, delayed, and examined from every angle, but once the evidence converges, definitions follow. This process can appear abrupt from the outside, but internally it is often long overdue. The redefinition of a planet therefore did not represent a change in the solar system. It represented a change in honesty. Adding Eris as a planet would have preserved familiarity at the cost of coherence. Redefining the term preserved coherence at the cost of familiarity. Physics consistently chooses coherence. Another reason Eris forced redefinition rather than addition lies in scalability. A scientific definition must work not only for known cases, but for future ones. It must remain valid as observations improve. A definition that requires constant amendment every time a new object is discovered is not a definition. It is a placeholder. By redefining planet in terms of orbital dominance, astronomers created a criterion that scales naturally. It applies to the inner solar system, the outer solar system, and planetary systems around other stars. It does not depend on distance, discovery era, or cultural attachment. This universality matters. Physics seeks laws and classifications that apply everywhere, not just locally. If Eris forced planetary science to adopt a definition that works beyond our solar system, then it improved the discipline rather than destabilized it. There is also a deeper conceptual reason why addition was not sufficient. Addition implies that the category itself is sound, merely incomplete. Redefinition implies that the category was misaligned with reality. Eris demonstrated the latter. The old definition of a planet, informal and historically inherited, had never been tested against a large population of similar objects. It worked only because the sample size was small. Once the sample size grew, flaws became obvious. Eris increased the sample size in exactly the wrong way for the old definition to survive. In this sense, Eris functioned like a stress test. It exposed where assumptions broke down. Stress tests are valuable precisely because they reveal limits. It is sometimes argued that Eris could simply have been labelled a planet alongside Pluto, and the public could have adapted. But this argument misunderstands the role of classification in science. Classification is not meant to accommodate public comfort. It is meant to reflect structure. If scientists had added Eris without redefining the category, they would have been postponing the same problem, not solving it. Each subsequent discovery would reopen the debate. The solar system would become less intelligible, not more. Redefinition solved the problem once cleanly. It also clarified the status of the Kuiper Belt itself. Without redefinition, the Kuiper Belt would be a region filled with planets that do not behave like planets. With redefinition, it becomes a population of objects with shared dynamical characteristics, distinct from planets in the inner and giant planet regions. This distinction enhances understanding rather than diminishing it. The introduction of the term dwarf planet is often misunderstood as a compromise. In physics terms, it is not. It is a recognition that internal structure and external influence are different questions. An object can be large enough for gravity to shape it into a sphere and still be dynamically subordinate. That distinction existed long before the term was coined. The term simply made it explicit. Eris fit naturally into this refined framework. It did not need to be forced into a planetary role that did not match its behaviour. It gained a classification that describes what it actually is. This is why Eris did not become the 10th planet. The 10th planet would have needed to behave like the first 8. Eris does not. The redefinition also resolved a lingering inconsistency. Under the old logic, moons larger than planets were excluded from planetary status based solely on what they orbit. That exclusion was already a sign that the definition was incomplete. By focusing on orbital dominance rather than orbit target, the new framework avoids such contradictions. Physics prefers definitions that reduce special cases. Eris eliminated the last justification for treating Pluto as 1. There is a tendency to frame this change as loss, as though something was taken away. From a scientific perspective, nothing was lost. Pluto did not change. Eris did not change. The solar system did not change. What changed was the precision with which these objects were described. Precision is progress in science. It is also worth noting that redefining the term did not diminish the importance of studying Pluto or Eris. On the contrary, it highlighted their role as representatives of a major dynamical regime. Their classification draws attention to the Kuiper Belt as a fundamental component of the solar system rather than a footnote. If Eris had been added as a planet, it would have remained an oddity at the end of a list. By forcing redefinition, it helped transform the list into a system. This transformation aligns planetary science with how physics approaches complexity everywhere else. When new data reveal that old categories no longer capture essential differences, categories are refined. This is not revisionism, it is responsibility. Eris did not ask to be included. It demanded consistency, and consistency required acknowledging that the solar system contains multiple gravitational regimes, not a single sequence of privileged objects. Planets are one regime. The Kuiper Belt population is another. Treating them differently is not discrimination. It is description. Comparing Pluto and Eris through mass ratios and orbits removes almost all remaining ambiguity, because numbers do not negotiate. When two objects are placed side by side within the same mathematical framework, sentiment falls away and structure becomes visible. Pluto and Eris are often spoken about as rivals, as if one displaced the other, but physics does not frame the comparison that way. Instead, it asks a simpler and more decisive question. Given their masses, their orbits, and their gravitational environments, do these objects occupy the same dynamical role? And does that role resemble what planets do elsewhere in the solar system? The answer emerges not from any single measurement, but from how those measurements combine. Start with mass, because mass is the source of gravitational influence. Pluto's mass is approximately 1.3 times 10 to the power of 22 kilograms. Eris is slightly more massive, at about 1.67 times 10 to the power of 22 kilograms. The difference is real, but it is modest. Eris outweighs Pluto by roughly 27%. In everyday terms, that sounds significant. In planetary dynamics, it is not. Both masses fall squarely within the same regime, far below the threshold required to dominate an orbital zone at their distance from the Sun. This becomes clearer when those numbers are placed in context. Earth's mass is about 6 times 10 to the 24th power kilograms. Neptune's mass is roughly 1 times 10 to the 26th power kilograms. Compared to these bodies, Pluto and Eris are minuscule. They are closer in mass to large moons than to planets. More importantly, they are close to each other in mass, which means they should behave similarly if mass is the controlling factor, and they do. Mass ratios matter more than absolute mass. In orbital dynamics, what determines dominance is not how heavy an object is in isolation, but how heavy it is compared to everything else in its neighbourhood. Earth outweighs the combined mass of near-Earth objects by an enormous factor. Jupiter outweighs the asteroid belt by orders of magnitude. Pluto and Eris do not outweigh the populations they belong to in any comparable way. When scientists calculate planetary discriminants or similar metrics, Pluto and Eris fall into the same low dominance category. There is no gap between them. The gap exists between them and the 8 major planets. This separation is not subtle. It spans several orders of magnitude. No amount of fine-tuning or reinterpretation bridges it. Orbital properties reinforce this conclusion. Pluto's orbit is eccentric, with a value of about 0.25. Eris's orbit is even more eccentric, closer to 0.44. Both values are far higher than those of the major planets, whose eccentricities cluster near 0. These elongated orbits indicate histories shaped by scattering and resonance, rather than by calm accretion within a dense disk. Inclination tells the same story. Pluto's orbit is tilted by about 17 degrees relative to the ecliptic. Eris's inclination is even more extreme at roughly 44 degrees. These are not small deviations, they are signatures of dynamical excitation. Objects that grow into dominant planets do not typically retain such inclinations. Their interactions with the surrounding material damp them out. The fact that Eris is more inclined and more eccentric than Pluto does not elevate Eris. It simply places it deeper into the same population regime. Both objects clearly reside outside the orderly plane of planetary dominance. Their differences are differences of degree, not of kind. Orbital period provides further context. Pluto takes 248 Earth years to orbit the Sun. Eris takes approximately 558 years. These long periods reflect their great distances and the weak gravitational environment they inhabit. Encounters are rare. Evolution is slow. Clearing is ineffective. The physics predicts that objects in this regime will remain members of populations indefinitely. Another critical comparison lies in orbital control. Pluto is locked into a 3-to-2 resonance with Neptune. This resonance protects Pluto from close encounters but also demonstrates dependence. Neptune dictates the terms, Pluto complies. Eris, by contrast, is not currently in a strong low-order resonance with Neptune, but this does not imply greater autonomy. Instead, Eris occupies a scattered or detached orbit that reflects past interactions and long-term weak coupling. In both cases, Neptune is the dominant architect. Pluto's resonance shows direct control, Eris's detachment shows indirect shaping. Neither object exerts comparable influence on Neptune or on the broader Kuiper Belt. Their orbital histories differ in detail, but their dynamical status is the same. This distinction is essential. One might be tempted to argue that Eris, being slightly more massive and less tightly resonant, represents a different class. The mathematics does not support this. Both objects lack the mass to impose resonances of their own on a population. Both lack the ability to scatter rivals efficiently. Both persist because they avoid frequent encounters, not because they resolve them. Another way to compare Pluto and Eris is through their hill spheres, the regions around them where their gravity dominates over the Sun's tidal influence. Eris's hill sphere is slightly larger than Pluto's because of its greater mass and greater distance from the Sun. This difference allows Eris to retain its moon, just as Pluto retains its own. But hill sphere size does not scale up to orbital dominance. It defines local control, not regional authority. Both objects control their immediate surroundings and nothing more. This is an important point because it highlights why internal complexity and satellite systems do not determine planetary status. Pluto has a complex moon system. Eris has one as well. Many asteroids have moons. Local gravity is easy to achieve. System-wide influence is not. Comparing Pluto and Eris also clarifies why adding Eris as a planet would not have solved anything. If Eris were considered a planet because it is slightly more massive than Pluto, then Pluto's status would become arbitrary. The difference between them is too small to justify a categorical boundary. Any such boundary would be numerological rather than physical. Physics avoids boundaries drawn at arbitrary percentages. It looks for regime changes. There is no regime change between Pluto and Eris. There is a regime change between them and Neptune. Orbital stability further supports this. Both Pluto and Eris occupy stable orbits over billions of years, but their stability arises from different mechanisms than planetary stability. Their orbits are stable because they are dynamically isolated, not because they dominate. Planets are stable because they clear and control. Pluto and Eris are stable because they coexist and avoid. This difference becomes apparent in numerical simulations. When the outer solar system is modelled, removing Pluto or Eris has negligible effect on the overall structure. Removing Neptune fundamentally alters it. That asymmetry is the clearest possible expression of dominance. From a system's perspective, Pluto and Eris function as tracers, not drivers. Their orbits record the gravitational history of the outer solar system. They do not determine its future. Planets, by contrast, shape both history and future. Mass ratios make this explicit. Neptune is roughly 10,000 times more massive than Pluto. Jupiter is more than 1,000,000 times more massive. These ratios are not matters of degree. They define entirely different physical behaviours. The equations of motion respond accordingly. It is also worth noting that Pluto and Eris share compositional similarities that align with their dynamical classification. Both are rich in volatile ices. Both formed in cold environments. Both retained primitive material. Dominant planets tend to erase such signatures through differentiation and energetic processing. Population members preserve them. This preservation is another indication of their shared role. They are relics, not architects. Some discussions attempt to elevate Eris by pointing out that it is denser than Pluto. While density does matter for internal structure, it has little bearing on orbital dominance. Density affects whether an object differentiates, not whether it clears a neighbourhood. Mass and location remain decisive. When all of these comparisons are taken together, a consistent picture emerges. Pluto and Eris are siblings in a dynamical sense. They are not twins, but they are clearly members of the same family. Their differences tell us about variation within the family, not about separate categories. This is precisely why Eris forced a redefinition. The comparison left no room for a special exemption. Treating Pluto as a planet while denying Eris the same status would have required ignoring mass ratios, orbital behaviour and gravitational influence. Treating both as planets would have erased the distinction between dominance and coexistence. Physics chose the third option. It recognised Pluto and Eris as representatives of a distinct dynamical class. Importantly, this recognition does not diminish either object. It enhances their significance. By grouping them correctly, planetary science gained a clearer understanding of the outer solar system as a whole. Pluto and Eris became key examples rather than awkward edge cases. Their comparison also underscores an important lesson. Classification in physics is comparative, not absolute. An object's status depends on how it relates to others, not on its intrinsic properties alone. Pluto and Eris relate to each other far more closely than either relates to the 8 major planets. Once this relational view is adopted, the controversy dissolves. The conclusion follows directly from the numbers. Mass ratios align, orbital properties align, gravitational influence aligns. The only thing that does not align is tradition. Tradition has no term in the equations. Roundness feels intuitive, it feels decisive. When people imagine a planet, they imagine a sphere, smooth and self-contained, shaped by its own gravity into something balanced and complete. For a long time, that intuition quietly guided classification, even when it was not stated explicitly. If an object was large enough for gravity to pull it into a rounded shape, it seemed reasonable to treat it as a planet. Hydrostatic equilibrium, the physical condition that produces roundness, appeared to offer a clean dividing line. In practice, it did not. Hydrostatic equilibrium describes a balance between two forces acting within a body. Gravity pulls material inward, toward the center. Internal pressure, generated by the material's resistance to compression, pushes outward. When these forces balance at every point, the object settles into a shape that minimizes gravitational potential energy. For most objects large enough, that shape is close to a sphere, though rotation can distort it slightly into an oblate form. This condition is real. It is measurable. It tells us something important about an object's internal structure and history. But it tells us nothing about how that object behaves within a larger gravitational system. That distinction is where confusion begins. Hydrostatic equilibrium is an internal property. It depends on mass, composition, temperature, and material strength. Once an object crosses a certain size threshold, its own gravity overwhelms the rigidity of rock or ice and forces the body into a rounded shape. The threshold is not universal. Icy bodies reach hydrostatic equilibrium at smaller sizes than rocky ones. Temperature also matters. A warm object deforms more easily than a cold one. As a result, roundness appears across a wide range of solar system objects. Many moons are round. Some asteroids are nearly round. Several Kuiper Belt objects are round. Being spherical is not rare. It is a consequence of physics acting internally, not a marker of system-wide influence. This is why roundness alone cannot define a planet. If hydrostatic equilibrium were sufficient, then many moons would qualify as planets. Earth's moon is round. Jupiter's moon Ganymede is round and larger than Mercury. Saturn's moon Titan is round and more massive than Pluto. Yet no one seriously argues that these moons should be planets in their own right, because their behavior is clearly subordinate. They orbit planets. Their motion and long-term stability are controlled by something else. This reveals an important principle. Internal structure does not determine dynamical role. A body can be internally complex, layered, differentiated, and geologically active, and still be dynamically insignificant on a system scale. Hydrostatic equilibrium tells you that gravity has shaped the object itself. It does not tell you that the object shapes its environment. Planetary physics is concerned with the latter. When hydrostatic equilibrium was included in formal definitions, it was meant to ensure that planets were not small, irregular fragments. That criterion made sense as a minimum condition. A planet should be massive enough to behave like a self-gravitating body rather than a rubble pile. But treating that condition as sufficient blurred a crucial boundary. Roundness does not imply dominance. This becomes especially clear when examining the outer solar system. Objects like Pluto and Eris are round because their internal gravity is strong enough to overcome material strength. They are also cold and icy, which lowers the threshold for deformation. Achieving hydrostatic equilibrium was relatively easy for them. Achieving orbital dominance was not. The physics behind this difference is straightforward. Internal gravity scales with mass and size, external influence scales with mass relative to the environment and with distance from the sun. These scalings are not the same. An object can cross the internal threshold long before it crosses the external one. Pluto and Eris are perfect examples. Pluto's roundness tells us that it is massive enough to have differentiated, to have undergone geological processes, and to maintain a complex internal structure. All of that is true and scientifically important. None of it grants Pluto authority over its orbital region. The same is true of Eris. This is why the inclusion of hydrostatic equilibrium in planetary definitions had to be paired with other criteria. On its own, it groups together objects that behave very differently in a dynamical sense. Physics resists such grouping because it obscures cause and effect. Another reason roundness fails as a sole criterion is that it depends on composition. An icy body can become round at a much smaller size than a rocky one. This means that two objects of equal mass but different composition could fall on opposite sides of a roundness threshold. Classification would then depend on chemistry rather than gravitational role, which is not meaningful in a dynamical context. Even worse, the threshold itself is fuzzy. There is no sharp boundary where an object suddenly becomes spherical. There are transitional shapes. Some bodies are nearly round but not fully relaxed. Others are round in one dimension and distorted in another due to rotation. Deciding where to draw the line becomes subjective. Physics avoids subjective thresholds whenever possible. Orbital dominance, by contrast, produces clearer separation. The difference between an object that outweighs its neighbours by orders of magnitude and one that does not is unambiguous. That difference shows up in equations, simulations, and long-term evolution. Roundness does not. It is also important to recognise that hydrostatic equilibrium says nothing about formation pathway. Two round objects may have formed in completely different ways. One may have grown rapidly by accreting nearby material and clearing its zone. Another may have grown slowly within a population that never resolved into dominance. Internally they look similar. Externally they are not. Pluto and Earth illustrate this perfectly. Both are round. Both have layered interiors. Both show evidence of geological activity at some point in their histories. But Earth grew in a dense region, cleared its neighbourhood, and became a dominant planet. Pluto grew in a sparse region, never cleared its neighbourhood, and remained one object among many. Hydrostatic equilibrium cannot distinguish between these outcomes. This is why planetary physics treats internal and external gravity as separate questions. Internal gravity answers, what shape does this object take? External gravity answers, what does this object do to others? Planets must satisfy both in specific ways. When hydrostatic equilibrium is misunderstood as the defining feature of a planet, it leads to paradoxes. Moons become planets. Dwarf planets become indistinguishable from major planets. The solar system becomes a list of spherical bodies with no attention paid to how they interact. That picture does not match reality. The inclusion of hydrostatic equilibrium in refined definitions therefore serves a limited but important role. It ensures that the category excludes small, irregular debris. It acknowledges that a planet should be a body governed by its own gravity internally. But it does not elevate roundness above dynamics. Roundness is necessary but not sufficient. This balance is often lost in public discussions because roundness is easy to visualize. Dominance is not. You can see a sphere. You cannot easily see millions of years of gravitational scattering, but physics is not obligated to prioritize what is visually intuitive. Another subtle point is that roundness can persist even when dominance never existed. Once an object becomes spherical, it does not lose that shape simply because it fails to clear its neighbourhood. Internal gravity remains. Pluto did not stop being round when it failed to become a planet. Eris did not become round because of its classification. Shape and status are decoupled. This decoupling is essential for understanding why the term dwarf planet exists at all. It is not a compromise category. It is a recognition that internal and external criteria describe different aspects of physical reality. An object can satisfy one without satisfying the other. Dwarf planets are internally planet-like and externally population-like. This phrasing may sound informal, but it captures the physics precisely. Internally, their gravity is strong enough to shape them. Externally, their gravity is too weak to shape their environment. Both statements can be true simultaneously without contradiction. Eris and Pluto fall cleanly into this description. Their roundness reflects internal equilibrium. Their orbits reflect external subordination. The mismatch between these two aspects is what made older definitions unstable. It is also why Eris was so disruptive. If Pluto alone had been round at the edge of the solar system, it might have remained an exception indefinitely. Eris demonstrated that roundness in the Kuiper Belt was not exceptional, it was expected. That realization stripped roundness of its power as a distinguishing feature. Once roundness was recognized as common in the outer population, it could no longer serve as a criterion that separated planets from non-planets. It became a descriptive property rather than a classificatory one. Physics responded by placing roundness in its proper context. There is also an evolutionary aspect to hydrostatic equilibrium worth noting. Some objects may have reached equilibrium early in their history, when they were warmer, and then cooled and solidified. Their roundness is a fossil state. It does not imply ongoing activity or influence. Again, internal history and external role diverge. This fossilization is particularly relevant in the outer solar system, where temperatures are low and change is slow. Objects preserve early conditions. Planets closer to the Sun often erase them. The irony is that roundness, once seen as a hallmark of planetary status, turned out to be more common where planets are rare. The outer solar system contains many round bodies and very few dominant ones. The inner solar system contains few round bodies and several dominant ones. This inversion alone shows why roundness could not be the deciding factor. When all of this is taken together, the conclusion becomes unavoidable. Hydrostatic equilibrium describes what gravity does to an object itself. Planetary status depends on what gravity allows an object to do to others. These are related but fundamentally different questions. Pluto and Eris answered the first question affirmatively. They failed the second. That failure is not a deficiency, it is a classification. Once roundness was recognized as insufficient, attention returned to dynamics, where mass ratios, orbital structure, and long-term evolution provide clearer guidance. Internal gravity matters, but it does not override external behavior. This realization did not diminish the importance of hydrostatic equilibrium. It clarified its role. It became one criterion among several, not the deciding one. As the discussion continues, this clarity becomes increasingly important. The solar system contains many bodies that blur intuitive boundaries. Only by separating internal properties from external influence can those bodies be placed correctly. The dwarf planet category exists because physics needed a way to speak honestly about objects that satisfy some planetary conditions but not others, without forcing them into a role they do not play. It is not a compromise label, and it is not a demotion. It is a classification that emerges naturally once gravity is treated consistently at both internal and external scales. When the equations are followed all the way through, the need for such a category becomes unavoidable. At the most basic level, the dwarf planet category separates two very different questions that had long been conflated. The first question is whether an object is massive enough for its own gravity to shape it into a stable, self-gravitating body. The second question is whether that same object is massive enough to shape the space around it in a dominant way. These questions involve the same force, but they operate on very different scales. Internal gravity acts inward. It compresses material, overcomes rigidity, and drives an object toward hydrostatic equilibrium. Once this threshold is crossed, the object becomes round, layered, and capable of internal evolution. This process depends on composition, temperature, and size, but it does not depend on what else is nearby. An object can reach hydrostatic equilibrium in isolation or in a crowded region. The surrounding system is largely irrelevant. External gravity acts outward. It governs how an object interacts with its neighbours, how it exchanges energy and angular momentum, and whether it can reorganize its orbital environment. This process depends not just on mass, but on mass relative to other objects, distance from the star, encounter frequency, and timescale. It is inherently relational. For a long time, planetary language treated these two regimes as if they were inseparable. If an object was large and round, it felt natural to call it a planet. That intuition held when the solar system appeared simple. Once complexity revealed itself, intuition stopped being sufficient. The dwarf planet category is the point where internal and external gravity are explicitly disentangled. From a physics standpoint, this disentanglement is not optional. Without it, classification collapses into contradiction. Consider what happens if roundness alone defines a planet. Dozens of objects immediately qualify, many moons qualify, some asteroids nearly qualify. The category becomes bloated, and it stops correlating with any meaningful dynamical behaviour. Now consider what happens if orbital dominance alone defines a planet. The category becomes clean and predictive, but it no longer acknowledges an important physical distinction. Objects like Pluto and Eris are not rubble piles. They are not fragments. They are self-gravitating worlds with complex internal histories. Lumping them together with small irregular bodies also loses information. The dwarf planet category exists precisely to preserve both truths at once. In physics, when a single category tries to describe two incompatible behaviours, the solution is not to argue about edge cases. The solution is to split the category along physically meaningful lines. That is exactly what happened here. A dwarf planet is defined as an object that orbits the Sun, has enough mass for its own gravity to overcome material strength, and reach hydrostatic equilibrium, but has not cleared its orbital neighbourhood. Each part of this definition corresponds to a specific physical condition. None of them are aesthetic. None of them depend on discovery order or tradition. The first condition establishes context. The object is part of the solar system proper, not a moon orbiting another planet. This distinguishes system-level bodies from satellites, which are governed primarily by planetary gravity rather than stellar gravity. The second condition establishes internal physics. The object is massive enough to behave like a cohesive world rather than a loose aggregate. It has a meaningful internal structure shaped by gravity. The third condition establishes external physics. The object does not dominate its orbital region. It coexists with other bodies of comparable dynamical status. Taken together, these conditions define a regime that is physically distinct from both planets and small bodies. That regime exists whether or not a name is given to it. The category does not create the regime, it describes it. This is why the dwarf planet category is not arbitrary. It corresponds to a specific outcome of planetary formation and dynamical evolution. In regions where material was abundant and interactions were frequent, some bodies grew large enough to clear their neighbourhoods and became planets. In regions where material was sparse and timescales were long, bodies grew large enough to become round but not large enough to dominate. Those bodies became dwarf planets. Physics predicts both outcomes. Importantly, dwarf planets are not failed planets in the sense of having fallen short of a goal. There was no goal. Formation proceeds according to conditions. In the outer solar system, the conditions favoured population formation rather than hierarchy. Dwarf planets are the natural result of that environment, not incomplete versions of something else. The physics behind this can be traced directly to accretion theory. Accretion requires collisions. Collisions require proximity and relative motion. Far from the Sun, orbital speeds are low and volumes are large. Growth slows dramatically. Objects may reach the size where internal gravity dominates, but they do not reach the size where external dominance becomes possible within the lifetime of the system. This creates a gap between internal and external thresholds. That gap is exactly where dwarf planets live. Once this gap is acknowledged, the category becomes inevitable. Without it, classification would either overgeneralize or underrepresent physical reality. Another important aspect of the dwarf planet category is that it is stable under new discoveries. Finding additional dwarf planets does not force a redefinition of planets. The category is designed to accommodate a population. This scalability is a hallmark of good physical classification. By contrast, adding every new large object as a planet would require constant revision. The solar system would grow messier with each survey. The category of planet would lose explanatory power. Physics avoids definitions that degrade with data. The dwarf planet category also preserves continuity across systems. When astronomers study other planetary systems, they expect similar outcomes. Some regions will produce dominant planets. Other regions will produce populations of large, self-gravitating bodies that never clear their neighbourhoods. Having a category ready for those outcomes allows comparison without confusion. This universality matters. A physical definition should not depend on local quirks. It should apply wherever the same laws operate. The dwarf planet category satisfies that requirement. There is also an important statistical aspect. Dwarf planets are numerous compared to planets. This tells us something about formation efficiency. It tells us that clearing a neighbourhood is hard, and that dominance is the exception rather than the rule. Planets are special because they are rare outcomes, not because everything else is incomplete. In that sense, the dwarf planet category does not marginalise objects. It contextualises planets. Another point often missed is that dwarf planets are dynamically interesting precisely because they are not dominant. They preserve information that dominant planets erase. Their orbits, compositions, and internal structures record early conditions. Studying them reveals how the solar system formed in regions where growth stalled. Physics values such records. They are not secondary, they are complementary. The category also avoids forcing contradictory criteria into a single label. Without dwarf planets, one would have to choose whether roundness or dominance matters more. Physics shows that both matter, but for different reasons. The category allows both to be acknowledged without confusion. This is not unique to planetary science. Physics routinely uses intermediate categories to reflect regime changes. Matter transitions between phases. Stars are classified by mass ranges that correspond to different fusion processes. Galaxies are classified by structure and dynamics. In each case, categories exist because behaviour changes qualitatively across thresholds. Dwarf planets occupy such a threshold regime. It is also worth noting that the dwarf planet category does not imply inferiority. The word dwarf describes scale, not significance. In physics, dwarf stars are still stars. They fuse hydrogen. They obey stellar physics. They are not lesser versions of something else. The same logic applies here. A dwarf planet is still a planet-like body internally. It is not a small asteroid. It is not debris. It is a world governed by gravity at every level. What distinguishes it is not what it is, but what it cannot do externally. This external limitation is not a flaw. It is an outcome of environment. The category also helps avoid circular reasoning. If planet were defined by being round and being called a planet, then classification would be self-referential. By tying definitions to physical criteria, physics ensures that categories can be tested and revised if needed. The dwarf planet category passes this test. It can be applied consistently. It can be challenged with new data. So far, it has held up. Another advantage of the category is that it decouples scientific classification from emotional attachment. Pluto did not need to be defended or diminished. It needed to be described accurately. The dwarf planet category allows that description without pretending Pluto occupies a role it does not. The same applies to Eris and other similar objects. Their classification says nothing about their intrinsic interest or importance. It says something about their gravitational role. Once this is understood, the category stops feeling like a downgrade and starts feeling like a clarification. It also clarifies the structure of the solar system itself. Instead of a single ladder of importance, we see multiple regimes. Inner planets dominate locally. Giant planets dominate broadly. The Kuiper Belt contains populations and dwarf planets. Beyond that may lie even more detached populations. Each regime follows from the same laws applied under different conditions. Physics prefers this layered understanding because it scales naturally. As new regions are discovered or better understood, they can be placed within the framework without breaking it. The dwarf planet category is therefore not a patch. It is part of the framework. When Eris forced the issue, this framework was ready. The category already existed implicitly in the physics. Formalizing it simply made that implicit structure explicit. That formalization did not close discussion. It enabled it. With clear categories, scientists could compare objects meaningfully, test formation models, and refine simulations. This clarity is why the debate eventually settled within the scientific community, even if public discussion lingered. Physics moved on because the classification worked, and it continues to work. Classification in planetary physics does not begin with names, it begins with motion. Long before any label is applied, objects reveal what they are through how they move, how they interact, and how they respond to gravity over time. Categories are not imposed from the outside. They emerge from patterns that persist when equations are allowed to run forward for millions or billions of years. This is why dynamical behavior sits at the foundation of classification, not tradition, appearance, or convenience. In physics, a classification is useful only if it groups objects that behave similarly under the same rules. If two bodies respond differently to the same forces, placing them in the same category obscures understanding rather than improving it. Planetary science learned this lesson gradually, as the solar system revealed itself to be far more complex than early diagrams suggested. At first, classification followed observation. Bright objects that wandered against the background stars were grouped together. This was a reasonable starting point when data were limited. As soon as gravity became the explanatory framework, however, this observational grouping began to fracture. Objects that looked similar behaved differently. Objects that looked different behaved the same. The only reliable guide was motion. Dynamical behavior is descriptive in the deepest sense. It does not rely on snapshots. It relies on trajectories. A single image of an orbit tells you little. A simulation of that orbit over long timescales tells you almost everything. Does the orbit remain isolated, or does it interact strongly with others? Does it impose order or adapt to it? Does it erase competition or preserve it? These questions define dynamical class far more accurately than size or brightness ever could. This is why planetary physics treats time as an essential variable. A category that makes sense over a decade may fail over a billion years. Stability, dominance, and interaction only reveal themselves slowly. A system that looks orderly now may be metastable, slowly drifting toward chaos. A system that looks chaotic now may settle into long-term stability through resonance. Classification must account for this temporal dimension, or risk becoming misleading. When scientists examine the solar system through this lens, clear regimes appear. Inner planets occupy low eccentricity, low inclination orbits, and dominate their regions. Giant planets impose structure across vast distances, shaping debris belts and resonant populations. Beyond them lies a regime where dominance fails to emerge and populations persist. These regimes are not arbitrary. They are outcomes of gravitational evolution. Importantly, these regimes were not defined first and then filled with objects. They were inferred from behavior. Only after patterns were recognized did terminology follow. This order matters. It ensures that classification reflects reality, rather than forcing reality into preconceived boxes. One way this emergence becomes obvious is through numerical simulation. When physicists model the early solar system with large numbers of interacting bodies, they do not assign labels, they allow gravity to operate. After sufficient time, certain bodies grow large and clear their surroundings. Others remain embedded in populations. Still others are scattered or ejected. The resulting structure closely resembles the present solar system. Classification can then be read directly from outcomes. This is not a philosophical process. It is empirical. Change the initial conditions and you change the outcome. Increase the mass density in a region and planets form. Decrease it and populations persist. These transitions are not gradual. They occur when thresholds are crossed. Classification emerges at those thresholds. This is why planetary categories are best understood as regime markers rather than honorifics. A planet marks the regime where orbital dominance is achieved. A dwarf planet marks the regime where internal gravity is strong but external dominance is not. Small bodies mark the regime where neither threshold is crossed. Each category corresponds to a qualitatively different behaviour under gravity. Crucially, these categories remain meaningful even as new objects are discovered. When a new body is found, scientists do not ask what it should be called first. They ask how it moves. Does it belong to a known population? Does it follow the same statistical distributions? Does it interact in the same way? Only after these questions are answered does classification follow. This is why Eris did not destabilize planetary science. It fit cleanly into an existing dynamical regime. The category was already there, even if it had not yet been formalized. Eris did not require inventing new physics. It required acknowledging what the physics already implied. Classification emerging from behavior also explains why boundaries can feel uncomfortable. Nature rarely provides sharp edges. Dynamical regimes often transition gradually. There are objects near thresholds that exhibit mixed behavior. Physics accepts this ambiguity because it reflects underlying continuity. Categories remain useful as long as the regimes they represent are distinct in behavior, even if the boundaries are not infinitely precise. This tolerance for fuzziness is a strength, not a weakness. It allows classification to remain flexible without becoming arbitrary. The key requirement is that categories remain predictive. If knowing an object's category allows you to anticipate how it behaves, the classification is doing its job. In the case of planets and dwarf planets, this requirement is satisfied. Knowing that an object is a planet tells you that it dominates its orbit, clears its neighbourhood, and shapes surrounding structure. Knowing that an object is a dwarf planet tells you that it is internally self-gravitating but externally subordinate, embedded in a population. These expectations hold across known cases. Another reason dynamical behaviour drives classification is that dynamics connects present observations to past history. Orbits encode formation pathways. High inclinations and eccentricities point to scattering. Resonances point to migration. Circular coplanar orbits point to calm accretion. Classification based on these features therefore carries explanatory depth. It is not merely descriptive, it is historical. Names based on appearance cannot do this work. Two round objects may have entirely different histories. Two objects of different sizes may share the same dynamical past. Motion reveals these connections, classification follows. This approach also aligns planetary science with the rest of physics. In every branch of the discipline, regimes are defined by behaviour under governing equations. Laminar and turbulent flow are distinguished by how fluids behave, not by what they look like. Conductors and insulators are distinguished by how charges move, not by composition alone. Phases of matter are distinguished by symmetry and response, not by shape. Planetary classification follows the same logic. It distinguishes regimes of gravitational behaviour. Another important consequence of this approach is that classification remains open to revision if behaviour is misunderstood. If future observations reveal that a class of objects behaves differently than currently believed, definitions can be refined. This is not instability, it is responsiveness. Physics values categories that can evolve when evidence demands it. The alternative is rigidity. Rigid classifications resist change even when contradictions accumulate. Eventually they fail catastrophically. Planetary science avoided this outcome by allowing classification to follow dynamics rather than tradition. This is why debates about planetary status can feel emotional outside the scientific community, but resolve cleanly within it. The community is not attached to names, it is attached to consistency. Once a definition aligns with behaviour and continues to work across new discoveries, discussion naturally quiets. It is also why public discomfort does not signal scientific weakness. It signals a mismatch between intuitive categories and physical reality. Over time, intuition adapts. Physics does not wait. Classification emerging from dynamical behaviour also helps unify our understanding of planetary systems beyond our own. When astronomers observe debris disks around other stars, they infer unseen planets from gaps and resonances. These inferences rely entirely on dynamics. The same categories used in our solar system apply elsewhere, because they are grounded in behaviour, not in local quirks. This universality is a strong indicator that the classification scheme is physically meaningful. A scheme that works only locally is descriptive. A scheme that works universally is explanatory. It is also worth noting that dynamical classification reduces anthropocentric bias. The solar system is not organised for human convenience. It is organised by gravity. Allowing categories to reflect that organisation rather than human expectation brings description closer to truth. This does not make classification cold or detached. It makes it accurate. Accuracy is the foundation upon which deeper appreciation can be built. Once classification is understood as something that emerges from behaviour, not decree, the Pluto and Eris story becomes less about loss and more about clarity. Nothing was taken away. A mismatch was resolved. This clarity also reveals something broader. The solar system is not defined by a single organising principle everywhere. It contains multiple regimes coexisting under the same laws. Some regions produce hierarchy, others preserve populations. Classification mirrors this diversity. As the framework settles, attention naturally turns to what these categories tell us about the nature of science itself. Definitions change not because facts change, but because understanding deepens. Categories sharpen as behaviour becomes clearer. That process is not unique to planetary science. It is how physics advances everywhere. Observe behaviour, identify patterns, define regimes, test predictions, refine definitions. The story of Eris and Pluto is therefore not just about planets. It is about how scientific knowledge organises itself over time, guided by equations rather than expectations. And with that perspective in place, the remaining question is no longer why Pluto is not a planet, but what this episode reveals about how science handles complexity without losing coherence. The solar system became more accurate after 2006 not because anything physical changed, but because description finally caught up with behaviour. Accuracy in physics is not about preserving familiar structures, it is about reducing the gap between models and reality. For decades, that gap had been quietly widening. The reclassification that followed did not rearrange planets or alter orbits. It corrected language so that it aligned with what gravity had been doing all along. Before that point, the solar system was often presented as a finished inventory. The implication was subtle but powerful. 8 or 9 planets, neatly ordered, with everything else treated as secondary. This picture was simple enough to memorize, but simplicity is not the same thing as accuracy. As observational data accumulated, the list-based model required more and more exceptions to remain intact. Exceptions are often early warning signs in physics. They indicate that a framework is being stretched beyond what it can support. By the early 21st century, those warning signs were everywhere. Pluto's orbit was already known to be eccentric and inclined. Resonant populations beyond Neptune had been identified. The Kuiper Belt had emerged as a vast structure rather than a sparse afterthought. Numerical simulations showed that Pluto-like objects were expected, not rare. The solar system, as described by gravity, had outgrown the language used to describe it. Accuracy demands internal consistency. A model that treats objects with the same dynamical behaviour as fundamentally different is inconsistent. Before 2006, that inconsistency was embedded in the planetary definition. Pluto was treated as a planet despite behaving like a member of a population, while other objects with nearly identical behaviour were treated as something else simply because they had been discovered later. This asymmetry mattered. In physics, symmetry is not aesthetic. It is structural. When two systems obey the same equations under the same conditions, they must be described the same way, or the description becomes misleading. The solar system before 2006 violated this principle quietly but persistently. What changed was not a single vote or meeting, but the willingness to accept what the data had already established. By refining the definition of a planet to reflect orbital dominance, internal gravity and dynamical role, planetary science removed a contradiction that had been accumulating for decades. That removal increased accuracy immediately. Accuracy in this context means that categories began to correspond to physical regimes rather than historical artifacts. Planets became objects that dominate their orbital zones. Dwarf planets became objects that are internally self-gravitating but externally subordinate. Small bodies remained fragments and debris. Each category now mapped cleanly onto a different gravitational outcome. This mapping matters because it restores predictive power. Once categories align with behavior, knowing an object's classification allows reasonable expectations about how it formed, how it interacts, and how it will evolve. Before 2006, calling Pluto a planet did not allow such predictions. Pluto behaved nothing like the other planets. After reclassification, its behavior made sense within its category. The solar system also became more accurate because the revised framework scales properly. A good physical description must remain valid as more data are added. Prior to the change, every new Kuiper Belt discovery increased tension. Each object similar to Pluto raised the question of whether it should also be considered a planet. This trajectory leads to conceptual inflation, where a term expands until it loses meaning. After 2006, discoveries of additional dwarf planets did not destabilize the system. They fit where expected. The framework absorbed new data without strain. That stability is a hallmark of accuracy. Another aspect of improved accuracy lies in how formation is represented. The older picture implied that the solar system formed as a small set of privileged bodies with leftovers scattered around them. The refined picture shows something more nuanced. It shows that formation outcomes depend strongly on location, mass density, and time. Inner regions produce dominant planets. Outer regions produce populations. Both outcomes are legitimate and expected. This shift corrected a subtle but important misconception. It removed the idea that anything not classified as a planet must be incomplete or inferior. Instead, it revealed that different regions reach different endpoints under the same physical laws. Accuracy increased because the description became faithful to process rather than outcome ranking. The change also resolved inconsistencies involving moons. Prior to refinement, some moons were larger and more massive than planets, yet excluded solely because of what they orbit. This exclusion had no physical basis. By focusing on orbital dominance relative to the Sun, the refined framework avoided such contradictions. Moons were classified by their dynamical context, not by size alone. This consistency further increased accuracy. Another improvement came from clarity about boundaries. The solar system is not divided by sharp lines. Regions transition gradually. The refined framework acknowledges this by defining categories based on behavior rather than distance or enumeration. Accuracy does not require perfectly sharp edges. It requires that edges correspond to changes in regime. That condition is now satisfied. The role of time also became clearer. The refined description emphasizes that planetary status is not about a snapshot. It is about long-term evolution. An object must be able to clear its neighborhood within the age of the system to be considered dominant. This temporal criterion anchors classification to physical possibility rather than potential. Pluto is not a planet in waiting. It will never become one under a known physics. Recognizing that fact increased descriptive honesty. Public discomfort with the change often stemmed from the feeling that something familiar had been taken away. From a physical standpoint, nothing was removed. Pluto's properties did not change. Its scientific value did not change. What changed was the accuracy of the category used to describe it. Precision increased, ambiguity decreased. Accuracy also improved communication within science. Prior to the change, discussions about the outer solar system required constant caveats. Pluto had to be explained as a planet that did not behave like one. After refinement, those caveats disappeared. Pluto could be discussed as a dwarf planet whose behaviour matched expectations. Language became cleaner because it aligned with dynamics. This alignment matters in research contexts. When scientists build models, they rely on classifications to select assumptions. Treating Pluto as a planet could lead to inappropriate assumptions about its influence. Treating it as a population member leads to correct ones. The refined framework therefore improved not just terminology, but modelling accuracy. There is also an educational aspect to accuracy. Teaching the solar system as a system, rather than a list, encourages understanding rather than memorization. Students learn why objects behave differently rather than simply where they are placed. This shift fosters conceptual literacy instead of rote recall. Accuracy in education is not about reducing complexity. It is about presenting complexity honestly and accessibly. Another subtle improvement involves how the solar system is compared to others. Exoplanetary science relies heavily on dynamical interpretation. Planets are inferred from gaps, resonances and perturbations. A definition of planet that aligns with dynamical dominance allows direct comparison between systems. The refined framework therefore increased accuracy by making our solar system less parochial and more representative. The year 2006 often becomes a symbolic marker, but the underlying process was gradual. The solar system became more accurate because decades of observation, simulation and theory were finally reflected in classification. The change marked convergence, not rupture. It is also important to note that accuracy does not mean finality. The refined framework is accurate given current knowledge. If future discoveries reveal new regimes or challenge existing assumptions, definitions may evolve again. That possibility does not undermine accuracy, it defines it. Accuracy in physics is provisional but disciplined. It adjusts when evidence demands it. What did not happen after 2006 is just as important as what did. The solar system did not fracture into confusion. It did not lose coherence. It gained structure. Regions that had been awkward to explain became central. The Kuiper Belt transformed from a footnote into a defining component. Dwarf planets became a meaningful class rather than an afterthought. Accuracy also improved because the refined framework reduced anthropocentric bias. The older model privileged human discovery history. The refined model privileges physical behaviour. This shift brings description closer to how nature actually operates, independent of human perspective. The distinction between planets and dwarf planets also sharpened appreciation for dominance itself. Dominant planets are now understood as rare outcomes that require specific conditions. This rarity adds depth to their significance. They are not simply large objects. They are architects of structure. Recognizing that role enhances understanding of why the solar system looks the way it does. At the same time, the refined picture elevates the importance of non-dominant bodies. They are no longer dismissed as leftovers. They're recognized as records of early conditions. Accuracy increases because value is distributed according to explanatory relevance rather than status. The solar system after 2006 is therefore not smaller, it is richer. It contains fewer planets, but more understanding. Each category carries clearer meaning. Each object fits more naturally into its context. Accuracy also improved because the refined framework reduced the need for narrative workarounds. Before, Pluto required special explanation. After, it required none. It behaved exactly as expected for its category. When descriptions no longer require constant exception handling, accuracy has improved. This clarity extends to future discoveries. If a new object comparable to Pluto or Eris is found, it will not reopen debates. It will be classified straightforwardly based on its behaviour. The framework is prepared. That preparedness is a sign of maturity in a scientific model. Accuracy in physics is not measured by how comforting a description feels. It is measured by how well it survives contact with data. The post-2006 description has done exactly that. It has absorbed new observations without distortion. The solar system became more accurate because its description stopped pretending that all large round objects must occupy the same role. It acknowledged that gravity produces multiple outcomes. It allowed categories to reflect those outcomes instead of forcing them into a single mold. This accuracy does not close curiosity, it opens it. With a clearer framework, questions become sharper. Why did dominance emerge here and not there? How common are dwarf planet populations around other stars? What does the outer solar system tell us about early migration? These questions depend on accurate classification to be meaningful. Accuracy also brings calm. Once contradictions are resolved, debate loses urgency. Within the scientific community, the question of Pluto's status settled quickly because the framework worked. What remained was explanation, not argument. The refinement did not rewrite history, it clarified it. Pluto remains the same object it always was. Eris remains the same. The Sun remains central. The difference lies in how faithfully description mirrors dynamics. As this understanding settles, the solar system stops feeling like a list that lost an entry and starts feeling like a system that gained coherence. The story becomes less about subtraction and more about alignment. Eris tells us something quietly profound about planet formation physics, not because it is extreme or unusual, but because it is typical of an outcome that early models underestimated. For a long time, planet formation was imagined as a process with a single natural endpoint. Dust becomes rocks, rocks become planetesimals, planetesimals collide, and eventually a planet emerges, clearing its surroundings and settling into dominance. Eris demonstrates that this sequence is not universal. It shows that planet formation has multiple stable endings and that dominance is only one of them. To understand what Eris reveals, it helps to step back from classification entirely and focus on formation as a physical process. Planet formation begins in a disk of gas and dust surrounding a young star. Gravity pulls material inward, while angular momentum spreads it outward. Collisions occur, some destructive, some constructive. Over time, some bodies grow larger. The physics of this growth depends on local conditions, not on destiny. One of the most important of those conditions is surface density, the amount of solid material available in a given region of the disk. Close to the star, surface density is high. Material is packed into a relatively small volume. Orbital periods are short, so collisions are frequent. Growth proceeds rapidly. In these regions, runaway accretion is possible. Once an object becomes slightly larger than its neighbours, it begins to grow disproportionately fast, sweeping up material and becoming dominant. Farther from the star, everything changes. Surface density drops. Material is spread thinly across vast distances. Orbital periods lengthen dramatically, reducing collision frequency. Growth slows. Runaway accretion becomes difficult to sustain. Objects can grow, but they do so slowly and competitively, without a clear winner emerging before conditions change. Eris formed in this second environment. Its existence confirms that planet formation does not always resolve into hierarchy. In the outer solar system, growth reached a different equilibrium. Objects became large enough for their own gravity to matter internally, but not large enough to impose order externally. Formation stalled not because something went wrong, but because the environment dictated that outcome. This insight is critical because it reframes how physicists think about failed planets. Eris is not failed. It is complete. It reached the endpoint available to it given the available mass, timescale, and dynamical stirring of its region. The fact that it did not become dominant is not an absence. It is a result. Another key lesson from Eris concerns the role of planetary migration. Early in the solar system's history, the giant planets did not remain fixed. Interactions with the disk and with each other caused them to move. Neptune in particular migrated outward. This migration had profound consequences for the outer disk. Resonances swept through the region, capturing some objects, scattering others, and exciting inclinations and eccentricities across the population. Eris carries the imprint of this process. Its highly inclined, highly eccentric orbit cannot be explained by calm, in-place growth alone. It reflects a history of gravitational disturbance. This tells physicists that migration was not a minor adjustment. It was a dominant shaping force. Importantly, migration does not favour the emergence of a single dominant body in the outer disk. Instead, it disrupts growth. Objects that might otherwise have accreted peacefully are stirred, scattered, and separated. Collisions become less frequent and more destructive. Growth slows further. Eris's existence therefore supports models in which migration plays a central role in preventing planet formation beyond Neptune. This conclusion has broad implications. It suggests that the solar system's architecture is not accidental. The absence of a ninth dominant planet in the Kuiper Belt is not a mystery. It is a predicted outcome of migration combined with a low surface density. Eris is evidence that the process worked as expected. Another lesson comes from Eris's mass itself. Eris is one of the most massive objects in the Kuiper Belt, yet it is still far below the mass needed for dominance. This implies that there is a sharp drop-off in achievable mass beyond Neptune. Growth did not merely slow, it effectively plateaued. Many objects reach similar maximum sizes, creating a population with a characteristic upper limit. This plateau tells physicists something about accretion efficiency. It suggests that once objects in the outer disk reached a certain size, further growth became self-limiting. Their gravity was strong enough to perturb neighbours, but not strong enough to accrete them efficiently. Instead of merging, bodies avoided one another or were scattered apart. The system became dynamically hot, suppressing further accretion. Eris sits near the top of this mass distribution. Its size marks the ceiling of what the outer solar system could produce under those conditions. That ceiling is itself a valuable constraint on formation models. Any successful model must explain why growth stopped where it did. Eris also informs us about composition. Its high density compared to Pluto suggests a larger fraction of rock relative to ice. This points to compositional gradients in the outer disk, or to collisional histories that stripped volatiles. Either way, Eris shows that the outer solar system was not chemically uniform. Local conditions mattered. These compositional differences reinforce the idea that formation was not a single smooth process. It was messy, local, and sensitive to timing. Some objects formed earlier, when more gas was present. Others formed later. Some experienced significant collisions, others did not. Eris preserves evidence of this diversity. Another important implication concerns timescale. Eris's orbital period is more than 5 centuries long. At such distances, dynamical evolution is slow. This means that whatever state an object reaches early on is likely to persist. There is little opportunity for later reorganization. Eris is therefore a fossil, not just of formation conditions, but of early dynamical history. Planets closer to the Sun erase their past. Their strong gravity and frequent interactions smooth out irregularities. Orbits circularize, inclinations damp, small bodies are removed. The result is a clean system with little memory of its chaotic beginnings. The outer solar system, by contrast, retains that memory precisely because dominance never emerged. Eris teaches us that memory retention is a natural outcome of non-dominance. This has implications beyond our solar system. When astronomers observe debris disks around other stars, they often find structures that suggest incomplete clearing. Gaps, rings, and populations appear where planets may or may not exist. Eris tells us that such structures do not always imply hidden dominant planets. They may reflect population regimes similar to the Kuiper Belt. In other words, Eris helps calibrate interpretation. It reminds us that not every disk feature points to a planet. Some point to populations. Eris also challenges the assumption that planet formation is efficient by default. The traditional narrative often implies that given enough time, material will inevitably coalesce into planets. Eris contradicts this. It shows that formation can stall permanently. Given certain conditions, the system reaches a stable configuration that does not include dominant bodies. This has consequences for estimates of planet frequency. It suggests that many planetary systems may contain extensive populations of large, round bodies that never become planets. These systems would look very different from ours, not because they failed, but because they followed a different path. Eris therefore expands the space of possible outcomes in planet formation theory. It pushes against oversimplified models and forces inclusion of regimes where growth saturates. Another lesson lies in the relationship between internal and external gravity. Eris demonstrates that internal differentiation can occur independently of external dominance. This decoupling is important for understanding thermal evolution. Eris may have experienced internal heating, differentiation, and even transient activity despite never becoming a planet. Formation models must therefore account for internal evolution even in non-dominant bodies. This challenges the idea that geological complexity is exclusive to planets. Eris shows that complexity can arise wherever mass crosses the internal gravity threshold, regardless of dynamical role. Planet formation physics must therefore distinguish between internal evolution and system-level influence. The existence of Eris also reinforces the importance of stochasticity in formation. Small differences in early conditions can lead to divergent outcomes. Eris might have formed slightly closer to the Sun, or slightly earlier, or in a region with marginally higher density. Under those conditions, it might have grown larger. That it did not tells us that formation is sensitive to timing and location. This sensitivity implies that sharp boundaries between outcomes are rare. Instead, there are probabilistic distributions. Some regions produce planets, others produce dwarf planets, others produce belts. Eris occupies one point in that distribution, helping to define its shape. From a modelling perspective, Eris provides a valuable calibration point. Simulations that produce objects like Eris under realistic conditions are more likely to be accurate. Those that do not must be reconsidered. In this way, Eris constrains theory as effectively as any planet. There is also a broader philosophical lesson embedded in Eris's story. Planet formation is not a process that strives toward a specific ideal. It is a process governed by local physics. The outcome depends on what gravity is allowed to do under given constraints. Eris reminds us that nature does not privilege dominance. It permits it when conditions allow and withholds it when they do not. This realization removes teleology from planetary science. There is no intended number of planets. There is no preferred architecture. There are only outcomes. Eris's role in shaping definitions therefore reflects its deeper role in shaping understanding. It did not merely force a change in classification. It exposed assumptions about how formation should work. By contradicting those assumptions gently but decisively, it improved theory. It is also worth noting that Eris was discovered not at the beginning of this process, but near its culmination. The physics was already pointing in this direction. Eris arrived as confirmation, not revelation. That timing matters. It shows that scientific progress often depends on convergence rather than singular breakthroughs. Once Eris entered the picture, the remaining pieces fell into place. The Kuiper Belt was recognized as a population. Dwarf planets were recognized as a regime. Planet formation was recognized as outcome-dependent. The solar system became more coherent, not more fragmented. Eris therefore tells us that planet formation physics must be flexible enough to accommodate multiple stable outcomes. It must allow for dominance and coexistence. It must explain why some regions produce planets and others do not. Any theory that insists on a single path is incomplete. In that sense, Eris is not peripheral to planet formation theory. It is central. It occupies the space that theory must explain if it is to be considered successful. As understanding deepens, Eris also invites humility. It reminds us that the solar system still holds structures shaped by processes we are only beginning to fully understand. Even now, the outermost regions may contain objects that challenge current models. Eris prepares us for that possibility by showing that unexpected outcomes are not failures of nature, but tests of our assumptions. With this perspective, the story of Eris becomes less about demotion and more about expansion. It expands the range of known outcomes. It expands the scope of theory. It expands the solar system conceptually, even as the list of planets shrinks. Once Eris has taught us about formation, dynamics, and classification, the remaining question is not scientific but reflective. What does this episode reveal about how science changes, how humans respond to that change, and how understanding can grow without erasing meaning? At the edge of the Sun's gravitational reach, motion slows to a pace that feels almost detached from time as we experience it. Orbits stretch into centuries and millennia. Changes that would feel dramatic in the inner solar system unfold so gradually here that they can seem frozen when viewed across a human lifetime. This distant region is not a boundary marked by a line or a wall. It is a gradual thinning, where gravity still rules, but with a gentler hand, and where the outcomes of formation were never forced into a single, dominant shape. This is where Eris resides for most of its orbit, far from the Sun, far from the intense gravitational negotiations that sculpted the inner planets. Here, gravity still binds, still guides, still defines motion, but it does so without insisting on hierarchy. Objects persist without being absorbed. Populations remain without being cleared. The system does not resolve itself into a few rulers and many subordinates. Instead, it settles into coexistence. Understanding this region requires letting go of the expectation that every part of a planetary system should look like the part we inhabit. The inner solar system trained intuition to expect order, separation, and dominance. Each planet has its lane. Each lane is mostly empty. This architecture is real, but it is local. Farther out, the physics that produce that order weaken, not because gravity stops working, but because the conditions that amplify its effects are no longer present. Distance matters. At great distances from the Sun, orbital velocities are low. Encounters between objects are rare. When encounters do occur, they are gentle, slow, and often deflective rather than destructive. Growth through collision becomes inefficient. Clearing through scattering becomes ineffective. The system does not collapse into simplicity. It remains extended, distributed, and patient. Eris's long tilted orbit carries it through this region as both participant and witness. For most of its journey, it travels so far from the Sun that the light it receives is faint and distant. Temperatures remain extremely low, internal processes slow, external interactions become almost negligible. Yet gravity still holds Eris firmly. Its orbit is bound. Its path is predictable. It belongs to the solar system as surely as any planet, even if its role within that system is very different. This distinction between belonging and dominating is one of the quiet lessons of the outer solar system. An object does not need to command its environment to be part of the system. It needs only to remain gravitationally bound. Eris does this effortlessly. Its motion is stable over timescales that dwarf human history. It will continue its slow circuit long after the inner planets have changed in ways we can only speculate about. At this distance, the Sun's gravity defines a vast, diffuse sphere of influence. It weakens with distance, but it does not vanish. Even objects thousands of astronomical units away still feel its pull, though so faintly that other forces can begin to compete. The outer reaches of the solar system blur into interstellar space not because gravity ends, but because its influence becomes comparable to that of passing stars in the galactic environment. Eris sits well within this reach, but far enough out to illustrate how different the solar system looks when dominance is no longer the organising principle. Here, the system is not arranged into tidy rows. It is layered, overlapping and incomplete in a way that is not a flaw, but a feature. Resting at this edge invites a different way of thinking about planetary systems altogether. Instead of asking how many planets there are, the more meaningful question becomes how gravity partitions space into regimes. Some regimes favour consolidation, others favour persistence. Some erase history, others preserve it. The outer solar system belongs to the last category. This preservation is subtle but profound. Because dominant planets did not emerge here, early conditions remain readable. Inclinations remain high, eccentricities remain large. Populations retain their diversity. Eris's orbit is not just a path, it is a record of the solar system's youth, written in angles and distances rather than in rock layers. In this sense, Eris and its neighbours are not peripheral to understanding the solar system. They are central to it. They show what happens when gravity is allowed to act without being amplified by dense material and frequent collisions. They reveal outcomes that are just as natural as planets, even if they are less familiar. There is a temptation to think of this region as unfinished, as if something is missing because it did not produce another planet. Physics does not support that view. Formation does not have a required endpoint. It has constraints. Where constraints allow dominance, planets form. Where they do not, populations persist. Both outcomes are complete. The quietness of the outer solar system reinforces this perspective. Nothing here is in a hurry. Eris does not race to complete an orbit. It does not encounter rivals often enough to reshape its path. Its future looks much like its past. Stability does not require simplicity. It requires balance, and balance is abundant here. This calm does not mean inactivity. Subtle processes continue. Long-term gravitational interactions with the giant planets slowly adjust orbits. Galactic tides exert tiny influences. Passing stars over immense spans of time may alter the outermost trajectories, but these changes accumulate so slowly that they feel almost theoretical when considered from within a single lifetime. In such an environment, classification loses its emotional weight. The difference between planet and dwarf planet feels less like a judgment and more like a description of context. Near the Sun, dominance matters because it shapes everything else. Far from the Sun, dominance rarely appears, and its absence shapes everything instead. Resting at this edge also reframes the Pluto and Eris story one last time. The debate was never about worth. It was about accuracy. Once accuracy was achieved, the system felt larger rather than smaller. The solar system gained depth. It gained layers. It gained a sense of gradation rather than abrupt endings. This expanded view also aligns more naturally with what astronomers observe around other stars. Many systems appear to host belts, disks, and populations rather than neatly spaced planets alone. The outer solar system, once seen as an oddity, now looks like a familiar pattern. Eris helps bridge that understanding by embodying the population regime so clearly. From this vantage point, the solar system feels less like a finished diagram and more like a living structure shaped by probabilities and constraints. Some regions resolved into order, others did not. Neither outcome is superior, they are complementary. The Sun's gravitational reach, extending far beyond the visible planets, defines a domain where these outcomes coexist. Inner worlds dominate, outer worlds persist. Between them lies a continuum of influence rather than a sharp boundary. As attention lingers here, the emotional intensity that once surrounded Pluto's status naturally fades. What remains is a clearer picture of how gravity organises space. Names matter less, roles matter more. Understanding replaces nostalgia without erasing it. Eris continues its slow journey, unaffected by debates, indifferent to labels. Its orbit will not change because of how it is classified. It will change only in response to forces acting over unimaginable spans of time. That indifference is not cold, it is instructive. It reminds us that scientific descriptions are tools, not possessions. They are meant to fit reality, not the other way around. When reality reveals new structure, descriptions adapt. Nothing essential is lost in that adaptation. Something essential is gained. At the edge of the sun's influence, this lesson feels easier to accept. There is no pressure here to simplify or to conclude. The system does not rush toward finality. It allows coexistence, variation, and unfinished patterns to persist indefinitely. This makes the outer solar system an appropriate place to rest, conceptually. Not because the story ends here, but because it no longer needs to argue. The physics has spoken quietly and consistently. The categories align with behaviour. The contradictions have dissolved. What remains is a solar system that feels broader and more honest. Fewer planets, yes, but more structure, more nuance. More room for worlds like Eris to exist without being forced into roles they never played. From this distance, the sun still anchors everything, but it does not insist on sameness. Its gravity allows diversity to flourish where conditions permit it. That allowance is part of the system's character. As this perspective settles, it becomes clear that the story of Eris and Pluto was never really about exclusion. It was about recognition. Recognition of different gravitational outcomes. Recognition of multiple ways a system can be complete. Resting here, at the edge of dominance, the solar system feels less like a list that needed correcting, and more like a landscape that needed describing. Once described accurately, it does not feel diminished. It feels expanded, and as that understanding drifts gently into place, there is no need to close the story tightly. The outer solar system continues, quietly, patiently, carrying worlds that orbit without ruling, shaped without shaping, bound without competing. Their motion does not seek resolution. It seeks balance. The same gravity that organizes the inner planets allows this region to remain open, extended, and unresolved in the most stable way possible. That balance is not a conclusion. It is a condition. And within that condition, the solar system keeps moving, unhurried, consistent, and vast enough to hold both dominance and coexistence at once, without requiring us to choose between them.